Warning: empty page. This page intentionally left blank. Switching and finite-automata theory understand the structure, behavior, and limitations of logic machines with this thoroughly updated 3rd edition. New topics include CMOS gates, logic synthesis, logic design for emerging nanotechnologies, digital system testing, asynchronous circuit design. The intuitive examples and minimal formalism of the previous edition are retained, giving students a text that is logical and easy to follow, yet rigorous. Kohavi and Ja begin with the basics and then cover combinational logic design and testing before moving on to more advanced topics in finite-state machine design and testing. The theory is made easier to understand with 200 illustrative examples, and students can test their understanding with over 350 end-of-chapter review questions. Zvi Kohavi is Executive Vice President and Director General at Technion Israel Institute of Technology. He is Professor Emeritus of the Computer Science Department at Technion, where he held the position of Sir Michael and Lady Sobel Chair in Computer Engineering and Electronics. Niraj K. Ja is a professor at Princeton University and a fellow of the IEEE and ACM. He is a recipient of the AT&T Foundation Award and NEC Preceptorship Award for Research Excellence, the NCR Award for Teaching Excellence, and Princeton's Graduate Mentoring Award. Warning: empty page. Switching and finite-automata theory 3rd edition. Zvi Kohavi, Technion Israel Institute of Technology. Niraj K. Ja, Princeton University. Cambridge University Press. Cambridge, New York, Melbourne, Madrid, Cape Town, Singapore, Sao Paulo, Delhi, Dubai, Tokyo. Cambridge University Press. The Edinburgh Building, Cambridge, CB2, 8RU, UK. Published in the United States of America by Cambridge University Press, New York. Information on this title: www.cambridge.org/9780521857482 www.cambridge.org. Copyright Z. Kohavi and N. Ja, 2010. This publication is in copyright. Subject to statutory exception and to the provision of relevant collective licensing agreements. No reproduction of any part may take place without the written permission of Cambridge University Press. First published in print format 2009, ISBN 13978-0-511-65824-2 ebook, NetLibrary. ISBN 13978-0-521-85748-2 hardback. Cambridge University Press has no responsibility for the persistence or accuracy of URLs for external or third-party internet websites referred to in this publication, and does not guarantee that any content on such websites is, or will remain, accurate or appropriate. Contents. Preface. Page 11. Part 1. Preliminaries. 1. Number systems and codes. 3. 1.1 Number systems. 3. 1.2 Binary codes. 10. 1.3 Error detection and correction. 13 Notes and references. 19 Problems. 20. 2 Sets, relations, and lattices. 23. 2.1 Sets. 23. 2.2 Relations. 25. 2.3 Partially ordered sets. 28. 2.4 Lattices. 30 Notes and references. 33 Problems. 33 Part 2 Combinational logic. 3. Switching algebra and its applications. 37. 3.1 Switching algebra. 37. 3.2 Switching functions. 44. 3.3 Isomorphic systems. 52. 3.4 Electronic gate networks. Asterisk operator. 57. 3.5 Boolean algebras. 58 Notes and references. 60 Problems. 61. Contents. 4. Minimization of switching functions. 67. 4.1 Introduction. 67. 4.2 The map method. 68. 4.3 Minimal functions and their properties. 78. 4.4 The tabulation procedure for the determination of prime implicants. 81. 4.5 The prime implicant chart. 86. 4.6 Map entered variables. 93. 4.7 Heuristic two-level circuit minimization. 95. 4.8 Multi-output two-level circuit minimization 97 notes and references 100 problems 1015 logic design 108 5.1 design with basic logic gates 108 5.2 logic design with integrated circuits 112 5.3 NAND and NOR circuits 125 5.4 design of high-speed adders 128 5.5 metal oxide semiconductor MOS, transistors and gates, 132. 5.6 Analysis and synthesis of MLES networks, 135 notes and references, 143 problems, 144 6 multi-level logic synthesis, 151 6.1 technology-independent synthesis, 151. 6.2 Technology, mapping 162 notes and references, 169 problems 177 Threshold logic for nanotechnologies, 173 7.1 Introductory concepts, 173. 7.2 Synthesis of threshold networks 181 notes and references, 200 problems 2028 Testing of combinational circuits, 206 8.1 Fault models, 206 8.2 Structural testing, 212 228.3 Testing IDDQ. 8.4 Delay fault testing 224 8.5 Synthesis for testability 232 8.6 Testing for nanotechnologies 250 notes and references 254 problems 257 7 Contents Part 3 Finite-state machines 9 Introduction to synchronous sequential circuits and iterative networks 265 9.1 Sequential circuits Introductory example 265. 9.2 The finite-state model, basic definitions 269 9.3 Memory elements and their excitation functions 272 9.4 Synthesis of synchronous sequential circuits 280. 9.5 An example of a computing machine 293 9.6 Iterative networks 296 notes and references 300 problems 310 capabilities, minimization and transformation of sequential machines 307. 10.1 The finite-state model, further definitions 307 10.2 Capabilities and limitations of finite-state machines 309 10.3 State equivalence and machine minimization 311. 10.4 Simplification of incompletely specified machines 317 notes and references 330 problems 330 11 asynchronous sequential circuits 338 11.1 modes of operation 338 11.2 hazards 339 11.3 Synthesis of SiC fundamental mode circuits 346 11.4 Synthesis of burst mode circuits 358 notes and references 363 problems 365 12 Structure of sequential machines 372 12.1 Introductory example 372 12.2 State assignments using partitions 375 12.3 The lattice of closed partitions 380 12.4 Reduction of the output dependency 383 12.5 Input independency and autonomous clocks 386 12.6 Covers and the generation of closed partitions by state splitting 388 12.7 Information flow in sequential machines 395 12.8 Decomposition, asterisk operator 404 12.9 Synthesis of multiple machines 413 Notes and references 418 Problems 419 8 Contents 13 State identification experiments and testing of sequential circuits 431 13.1 Experiments 431 13.2 Homing experiments, 435 13.3 Distinguishing experiments, 439 13.4 Machine identification, 440 13.5 Checking experiments, asterisk operator, 442 13.6 Design of diagnosable machines, 448 13.7 Alternative approaches to the testing of sequential circuits, 453 13.8 Design for testability, 458 13.9 Built-in self-test, BSD, 461 Appendix 13.1 Bounds on the length of synchronizing sequences. 464 Appendix 13.2a Bound on the length of distinguishing sequences. 467 Notes and references. 467 Problems. 468. 14 Memory, definiteness, and information losslessness of finite automata. 478 14.1 Memory span with respect to input-output sequences, finite memory machines. 478. 14.2 Memory span with respect to input sequences, definite machines. 483 14.3 Memory span with respect to output sequences. 488. 14.4 Information lossless machines, asterisk operator. 491 14.5 Synchronizable and uniquely decipherable codes. 50 for Appendix 14.1 The least upper bound for information losslessness of finite order. 510 Notes and references. 512 Problems. 513 15 Linear, sequential machines. 523 15.1 Introduction. 523 15.2 Inert linear machines. 525 15.3 Inert linear machines and rational transfer functions. 532. 15 for the general model. 537 15.5 Reduction of linear machines. 541 15.6 Identification of linear machines. 550. 15.7 Application of linear machines to error correction. 556 Appendix 15.1 Basic properties of finite fields. 559 Appendix 15.2 The Euclidean algorithm. 561 Notes and references. 562 Problems. 563. 16 Finite-state recognizers. 570 16.1 Deterministic recognizers. 570 16.2 Transition graphs. 572. Content 16.3 Converting non-deterministic into deterministic graphs. 574 16.4 Regular expressions. 577 16.5 Transition graphs, recognizing regular sets. 582. 16.6 Regular sets corresponding to transition graphs, asterisk operator. 588. 16.7 Two-way recognizers. 595 Notes and references. 601 Problems. 602 Index. 608. 6. 6. One. Chapter 1 Number Systems and Codes. This chapter deals with the representation of numerical data, with emphasis on those representations that use only two symbols, 0 and 1. Described are special methods of representing numerical data that afford protection against various transmission errors and component failures. 1.1 Number systems. Convenient as the decimal number system generally is, its usefulness in machine computation is limited because of the nature of practical electronic devices. In most present digital machines, the numbers are represented and the arithmetic operations performed in a different number system called the binary number system. This section is concerned with the representation of numbers in various systems and with methods of conversion from one system to another. Number representation. An ordinary decimal number actually represents a polynomial in powers of 10. For example, the number 123.45 represents the polynomial. 123.45 is equal to 1 times 102 plus 2 by 101 plus 3 by 100 plus 4 times 10 minus 1 5 times 10 minus 2 plus This method of representing decimal numbers is known as the decimal number system, and the number 10 is referred to as the base, or radix, of the system. In a system whose base is b, a positive number n represents the polynomial equals plus n a0 b0 equals q minus 1I equals minus pab, where the base b is an integer greater than 1 and the a's are integers in the range 0 less than or equal to ai less than or equal to b minus 1. The sequence of digits aq minus 1, aq minus 2, a0 constitutes the integer 3. Number systems and codes table 1.1 representation of integers base 2 4 8 10 12 0 0 0 0 0 0 0 0 0 0 0 1 1 1 1 1 0 0 1 0 2 2 2 2 0 0 1 1 3 3 3 3 0 110 4 4 4 0 1 0 1 11 5 5 5 0 1 1 0 12 6 6 6 0 1 1 1 13 7 7 7 1020 10 8
8 1021 11 9 9 1010 22 12 10 alpha 1011 20
8 1001 21 11 99 1010 22 12 10 alpha 1011 23 13 11 beta 1130 14 12 10 1101 31 15 13 11 1110 32 16 14 12 1111 33 17 15 13. Part of n, while the sequence AP constitutes the fractional part of digits in the fractional and integer A1 A2. And thus, P and Q designate the number parts, respectively. The integer and fractional parts are usually separated by a radix point. The digit AP is referred to as the least significant digit.
The digit a minus p is referred to as the least significant digit, while aq minus 1 is called the most significant digit. When the base b equals 2, the number representation is referred to as the binary number system. For example, the binary number 1101.01 represents the polynomial 23 22 21 20. 2 minus 1 2 minus 2 1101.01 is equal to 1 times plus 1 times plus 0 times plus 1 times plus 0 times 1 times plus, that is 3 1101.01 ai 2I equals I equals minus 2, where 1 and 0 equals a0 equals a2 equals a3 equals n and base b is equals a1 equals n b a minus 2 a minus 1. A number usually denoted. Whenever the base is not specified, base 10 is implicit. Table 1.1 shows the representations of integers 0 through 15 in several number systems. The complement of a digit a, denoted a, in base b is defined as a equals b minus 1 minus a. That is, the complement is the difference between the largest digit in base b and digit a. In the binary number system, since b equals 2, 0 is equal to 1, and 1 is equal to 0. 1.1 number systems. In the decimal number system, the largest digit is 9. Thus, for example, the complement 1 of 3 is 9 minus 3 is equal to 6. Conversion of bases. Suppose that some number n, which we wish to express in base b2, is presently expressed in base b1. In converting a number from base b1 to base b2, it is convenient to distinguish between two cases. In the first case, b1, b2, and consequently base b2 arithmetic can be used in the conversion process. The conversion technique involves expressing number n, b1 as a polynomial in powers of b1 and evaluating the polynomial using base b2 arithmetic. Example: we wish to express the numbers 432.2, 8 and 1101.01, 2 in base 10. Thus, 82, 81, 88 minus 1, 432.2, 8 equals 4 times plus 3 times plus 2 times plus 2 times is equal to 1 times 23 plus 1 times 22 plus 0 times 21 is equal to 1 times 20, 1101.01. 2 plus 0 times 2 minus 1 plus 1 times 2 minus 2 equals 13.25, 10. In both cases, the arithmetic operations are done in base 10. When B1 and B2, it is more convenient to use base B1 arithmetic. The conversion procedure will be obtained by considering separately the integer and fractional parts of n. Let n b1 be an integer whose value in base b2 is given by 222 and b1 equals plus plus a1 b1 a0 b0 2. To find the values of the a's, let us divide the above polynomial by b2 plus a0 and b1 22 equals plus a1 b2 b2 q0. Thus, the least significant digit of n b2, i.e. a0, is equal to the first remainder. The next most significant digit, a1, is obtained by dividing the quotient q0 by b2, i.e. q0 plus a1, 2 equals plus b2 b2 b1 q1. The remaining a's are evaluated by repeated divisions of the quotients until qq minus 1 is equal to 0. If n is finite, the process must terminate.
1.
In the decimal system, the complement is also referred to as the nines complement. In the binary system, it is also known as the ones complement. Number systems and codes. Example: the above conversion procedure is now applied to convert 548, 10 to base 8. The re in the table below denote the remainders. The first entries in the table are 68 and 4, corresponding, respectively, to the quotient q0 and the first remainder from the division, 548 eighths, 10. The remaining entries are found by successive division. Chiri 68 4 equals A0, 4 equals A180 equals A211 equals A3. Thus, 548, 10 equals 1044, 8. In a similar manner, we can obtain the conversion of 345, 10 to 1333, 6, as illustrated in the table below. Chiri 57 3 equals A0, 3 equals A193 equals A211 equals A3. Indeed, 1333, 6 can be reconverted to base 10, i.e. 63, 62, 61, 60. 1333, 6 equals 1 times plus 3 times plus 3 times plus 3 times equals 345. If n b1 is a fraction, a dual procedure is employed. It can be expressed in base b2 as follows: 2 minus p2, and b1 equals plus a minus pb. The most significant digit, a minus 1, can be obtained by multiplying the polynomial by b2. 2 minus p plus 1 2, and b1 equals plus b2 a minus 1, a minus pb. If the above product is less than 1, then a minus 1 equals 0, if the product is greater to the integer part of the product. The than or equal to 1, then a minus 1 is equal. Next most significant digit, a minus 2, is found by multiplying the fractional part of the above product part by b2 and determining its integer part, and so on. This process does not necessarily terminate, since it may not be possible to represent the fraction in base b2 with a finite number of digits. (1.1) Number systems example: to convert 0.3125, 10 to base 8, find the digits as follows. 0.3125 times 8 is equal to 2.5000, hence 2 times 8 equals a minus 1 0.5000, 4.0000, hence 4. A minus 2. Thus, 0.3125, 10 equals 0.248. Similarly, the computation below proves that 0.375, 10 equals 0.0112.
0375 2 rovnítko 0750.
0.375 times 2 equals 0.750, hence 0 times 2 equals a 1 0.750 1.500, hence 1 times 2 equals A2 0.5001.000, hence 1. A3. Example to convert 432.354, 10 to binary, we first convert the integer part and then the fractional part. For the integer part we have GRI 216 0 equals A0 0 equals A1 108 0 equals A2 54 0 equals A3 27 1 equals A4 13 1 equals A5 6 0 equals A6 3 1 equals A7 1 1 equals A8, hence 432, 10 equals 110110000, 2. For the fractional part we have times equals 0.3542 0.708, hence 0, times 2 equals A1 A2 0.708 1.416, hence 1, times 2 equals A3 0.416 0.832, hence 0, times 2 equals A4 0.832 1.664, hence 1, times 2 equals A5 0.664 1.328, hence 1. Times 2 equals A6 0.328 0.656, hence 0, equals A7 1, etc. Consequently, 0.354, 10 equals 0.010101, 2. The conversion is accuracy. In our example, reconversion to base 10 usually carried up to the desired shows that 110110000.010101, 2 equals 432.3515, 10. Number systems encodes table 1.2 elementary binary operations bits A B sum A and B carry difference A B borrow product A B 001010101001010101000000001. A considerably simpler conversion procedure may be employed in converting octal numbers, i.e., numbers in base 8, to binary and vice versa. Since 8 equals 23, each octal digit can be expressed by 3 binary digits. For example, 6, 8 can be expressed as 110, 2, etc.
Since 8 is equal 00001. A considerably simpler conversion procedure may be employed in converting octal numbers, i.e., numbers in base 8, to binary and vice versa. Since 8 is equal to 23, each octal digit can be expressed by 3 binary digits. For example, 6, 8 can be expressed as 110, 2, etc. The procedure of converting a binary number into an octal number consists of partitioning the binary number into groups of 3 digits, starting from the binary point, and to determine the octal digit corresponding to each group. Example, 123.4, 8 equals 1,010,011.100, 2, 1010,110,0101, 2 equals 1,010,110.010,100 equals 126.24, 8. A similar procedure may be employed in conversions from binary to hexadecimal, base 16, except that 4 binary digits are needed to represent a single hexadecimal digit. In fact, whenever a number is converted from base B1 to base B2, where B2 equals book 1, k digits of that number, when grouped, may be represented by a single digit from base B2. Binary arithmetic. The binary number system is widely used in digital systems. Although a detailed study of digital arithmetic is beyond the scope of this book, we shall present the elementary techniques of binary arithmetic. The basic arithmetic operations are summarized in Table 1.2, where the sum and carry, difference and borrow, and product are computed for every combination of binary digits, abbreviated bits, 0 and 1. For a more comprehensive discussion of computer arithmetic, the reader may consult 2. Binary addition is performed in a manner similar to that of decimal addition. Corresponding bits are added, and if a carry 1 is produced, then it is added to the binary digits at the left. 1.1 number systems example the addition of 15.25, 10 and 7.50, 10 in binary proceeds as follows. 1,111 carries of 1,111.01 equals 15.25, 10 plus 111.10 equals 7.50, 10 to 10,110.11 equals 22.75, 10. In subtraction, if a borrow of 1 occurs and the next left digit of the minuend, the number from which a subtraction is being made, is 1, then the latter is changed to 0 and subtraction is continued in the usual manner. If, however, the next left digit of the minuend is 0, then it is changed to 1, as is each successive minuend digit to the left which is equal to 0. The first minuend digit to the left, which is equal to 1, is changed to 0 and subtraction is continued. Example: the subtraction of 12.50, 10 from 18.75, 10 in binary proceeds as follows. 1 borrows of 1 10,000 and 10.11 equals 18.75, 10 minus 1,100.10 equals 12.50, 10 110.01 equals 6.25, 10. Just as with decimal numbers, the multiplication of binary numbers is performed by successive addition while division is performed by successive subtraction. Example: multiply the binary numbers below. 11,001.1 equals 25.5, 10 times 110.1 equals 6.5, 10 110,011 0 0 0 0 0 0 110,000 and 11 110 0 1 110,000,000 100,000 101.11 equals 165.75, 10. Number systems and codes example: divide the binary number 100, 010, 0110 by 11,001. 10110 quotient 11,001 100, 010, 0110 11,001 0 0 10 0 10 1 11,001 0 0 110 01 110 010 0 0 0 0, remainder 1.2 binary codes. Although the binary number system has many practical advantages and is widely used in digital computers, in many cases it is convenient to work with the decimal number system, especially when the communication between human being and machine is extensive, since most numerical data generated by humans is in terms of decimal numbers. To simplify the problem of communication between human and machine, several codes have been devised in which decimal digits are represented by sequences of binary digits. Weighted codes. In order to represent the 10 decimal digits 0, 1, 9, it is necessary to use at least 4 binary digits. Since there are 16 combinations of 4 binary digits, of which 10 combinations are used, it is possible to form a very large number of distinct codes. Of particular importance is the class of weighted codes, whose main characteristic is that each binary digit is assigned a decimal weight, and, for each group of 4 bits, the sum of the weights of those binary digits whose value is 1 is equal to the decimal digit which they represent. If W1, W2, W3, and W4 are the given weights of the binary digits and X1, X2, X3, X4 the corresponding digit values, then the decimal digit n equals W4x4 plus W3x3 plus W2x2 plus W1x1 can be represented by the binary sequence x4, x3, x2, x1. The sequence of binary digits that represents a decimal digit is called a code word. Thus, the sequence x4, x3, x2, x1 is the code word for n. 3 weighted 4-digit binary codes are shown in Table 1.3. The binary digits in the first code in Table 1.3 are assigned weights 8, 4, 2, 1. As a result of this weight assignment, the code word that corresponds to each decimal digit is the binary equivalent of that digit, e.g., 5 is represented by A101 and so on. This code is known as the binary coded decimal, BCD. 1.2 Binary codes, Table 1.3 The code words x4, x3, x2, x1 for the decimal digits, and in 3 weighted binary codes, decimal W4, W3, W2, W1 digit, and 8421242164 minus 300000000000100010001000 1-810-00-111-110-910
Code.
For each code in Table 1.3, the decimal digit that corresponds to a given code word is equal to the sum of the weights in those binary positions that are ones rather than zeros. Thus, in the second code, where the weights are 2, 4, 2, 1, decimal 5 is represented by 1011, corresponding to the sum 2 times 1 plus 4 times 0 plus 2 times 1 plus 1 times 1 is equal to 5. The weights assigned to the binary digits may also be negative, as in the code 6, 4, 2, minus 3. In this code, decimal 5 is represented by 1011, since 6 by 1 plus 4 times 0 plus 2 by 1 minus 3 times 1 is equal to 5. It is apparent that the representations of some decimal numbers in the 2, 4, 2, 1, and 6, 4, 2, minus 3 codes are not unique. For example, in the 2, 4, 2, 1 code, decimal May 7th be represented by 1101 as well as 0111. Adopting the representation in Table 1.3 causes the codes to become self-complementing. A code is said to be self-complementing if the code word of the 9's complement of n, i.e., 9 minus n, can be obtained from the code word of n by interchanging all the ones and zeros. For example, in the 6, 4, 2, minus 3 code, decimal 3 is represented by 1001 while decimal 6 is represented by 0110. In the 2, 4, 2, 1 code, decimal 2 is represented by 0010 while decimal 7 is represented by 1101. Note that the BCD code 8, 4, 2, 1 is not self-complementing. It can be shown that a necessary condition for a weighted code to be self-complementing is that the sum of the weights must equal 9. There exist only 4 positively weighted self-complementing codes, namely 2, 4, 2, 1, 3, 3, 2, 1, 4, 3, 1, 1, and 5, 2, 1, 1. In addition, there exist 13 self-complementing codes with positive and negative weights. Non-weighted codes, there are many non-weighted binary codes, 2 of which are shown in Table 1.4. The XS3 code is formed by adding 0011 to each BCD code word. Number systems and codes, Table 1.4 Non-weighted binary codes, decimal digit XS 3 cyclic 00010101010101010101010101010101010101010101010101010101010101010101010101010101010101010101010101010101010 1-1-1-0-8-1-0-9-1-1-0-0-9-1-1-0-0-0-1-0-0 Table 1.5 Decimal numbers in the complete 4-bit gray code and in binary decimal gray binary number G3 G2 G1 G0 B3 B2 B1 B0 00 0-0-0-0-0-0-0-1-0-0-0-1-0-0-0-1-0-0-0-0-1-1-4-0-1-1-0-0-1-0-0-50 1-1-1-0-1-0 1601010, 110701000, 111811001000, 911. 0110 110 1111111111 111010 11121010 1100 1310 111110 11410 0 111110 1510 0 0 1111. Thus, for example, the representation of decimal 7 in excess 3 is given by 0111 plus 0011 equals 1010. The excess 3 code is self-complementing and possesses a number of properties that made it practical in early decimal computers. In many practical applications, e.g., analog-to-digital conversion, it is desirable to use codes in which the code words for successive decimal integers differ in only one digit. Codes that have such a property are referred to as cyclic codes. The second code in Table 1.4 is an example of such a code. Note that in this, as in all cyclic codes, the code word representing the decimal digits 0 and 9 differ in only one digit. A particularly important cyclic code is the gray code. A 4-bit gray code is shown in Table 1.5, the feature that makes the cyclic 1.3 error detection and correction code useful is the simplicity of the procedure for converting from the binary number system into the gray code as follows. Let denote a code word in the n+1 th-bit gray code, and let gn, g2, g1, g0 designate the corresponding binary number, where the subscripts bn, b2, b1, b00, and n denote the least significant and most significant digits, respectively. Then, the ith digit gi can be obtained from the corresponding binary number as follows: 0, 1 equals by circle plus equals bn less than or equal to I less than or equal to n minus gi by plus 1, gn, where the symbol circle plus denotes the modulo 2 sum, which is defined as follows: 0 circle plus 0 is equal to 0, 1 circle plus 1 is equal to 0, 0 circle plus 1 is equal to 1, 1 circle plus 0 is equal to 1. For example, the gray code word that corresponds to the binary number 101101 is found to be 111011 in a manner indicated in the following diagram: B5, B4, B3, B2, B1, B0 plus 10111 111011. G5, G4, G3, G2, G1, G0. Thus, to convert from gray code to binary, start with the leftmost digit and proceed to the least significant digit, setting by equals gi if the number of ones preceding gi is even, and setting equals gi if the uneven number of ones. For example, the by odd. Note that 0 ones counts as gray code word 100. 1011 represents the binary number 111, 0010. The proof that the preceding conversion procedures does indeed work is left to the reader as an exercise. The n-bit gray code is a member of a class called reflected codes. The term reflected is used to designate codes which have the property that the n-bit code can be generated by reflecting the n-1 th-bit code, as illustrated in Figure 1.1. The 2-bit gray code is shown in Figure 1.1a. The 3-bit gray code, Fig. 1.1b, can be obtained by reflecting the 2-bit code about an axis at the end of the code and assigning a most significant bit of 0 above the axis and 1 below the axis. The 4-bit gray code is obtained in the same manner from the 3-bit code, as shown in Figure 1.1c. 1.3 Error detection and correction. In the codes presented so far, each code word consists of 4 binary digits, which is the minimum number needed to represent the 10 decimal digit. The n-bit gray code is a member of a class called reflected. 1.3 Error detection and correction. In the codes presented so far, each code word consists of 4 binary digits, which is the minimum number needed to represent the 10 decimal digits.
Such.
Number systems and codes. Figure 1.1 reflection of gray 0, 0, 0, 0, 0, 0, 0, 0, 0 codes. 0, 1, 0, 0, 1, 0, 0, 0, 1, 11, 0, 11, 0, 0, 11, 10, 0, 10, 0, 0, 10, 1, 10, 0, 110, 1, 11, 0, 111, 1, 0, 1, 0, 100, 1, 1, 0, 0, 0, 100. 1 1 1 1 1 1 1 1 trillion 100 billion 101 million 111,000 110 0 10 0 11 0 0 1 0 0 0 A, B, C. Codes, although adequate for the representation of decimal digits, are very sensitive to the transmission errors that may occur because of equipment failure or noise in the transmission channel. In any practical system, there is always a finite probability of occurrence of a single error. The probability that 2 or more errors will occur simultaneously, although non-zero, is substantially smaller. We, therefore, restrict our discussion mainly to the detection and correction of single errors. Error detecting codes. In a 4-bit binary code, the occurrence of a single error in one of the binary digits may result in another, incorrect but valid, code word. For example, in the BCD code, see above, if an error occurs in the least significant digit of 0110, then the code word 0111 results, and, since it is a valid code word, it is incorrectly interpreted by the receiver. If a code possesses the property that the occurrence of any single error transforms a valid code word into an invalid code word, it is said to be a single error detecting code. 2 error detecting codes are shown in Table 1.6. Error detection in either code in Table 1.6 is accomplished by a parity check. The basic idea in a parity check is to add an extra digit to each code word of a given code, so as to make the number of ones in each code word either odd or even. In the codes of Table 1.6, we have used even parity. The even parity BCD code is obtained directly from the BCD code of Table 1.3. The added bit, denoted P, is called the parity bit. The 2 out of 5 code consists of all 10 possible combinations of 2 ones in a 5-bit code word, with the exception 1.3 Error detection and correction. Table 1.6 Error detecting codes decimal even parity BCD 2 out of 5-digit 8421 P0 1247000000000 111000 111000 300 1100 1100 40 100 1100 1050 1010 10 60 11000 1170 11111000 1810000 10100 19100 100 of the code word for decimal 0. The 2 out of 5 code of Table 1.6 is a weighted code and can be derived from the 1, 2, 4, 7 code. In each of the codes in Table 1.6, the number of ones in a code word is even. Now, if a single error occurs, it transforms the valid code word into an invalid one, thus making the detection of the error straightforward. Although parity check is intended only for the detection of single errors, it, in fact, detects any odd number of errors and some even numbers of errors. For example, if the code word 10100 is received in an even parity BCD message, it is clear that the message is erroneous, since such a code word is not defined although the parity check is satisfied. We cannot determine, however, the original transmitted word. In general, to obtain an n-bit error-detecting code, no more than half the possible 2n combinations of digits can be used. The code words are chosen in such a manner that, in order to change one valid code word into another valid code word, at least 2 digits must be complemented. In the case of 4-bit codes, this constraint means that only 8 valid code words can be formed of the 16 possible combinations. Thus, to obtain an error-detecting code for the 10 decimal digits, at least 5 binary digits are needed. It is useful to define the distance between 2 code words as the number of digits that must change in one word so that the other word results. For example, the distance between 1010 and 0100 is 3, since the 2 code words differ in 3-bit positions. The minimum distance of a code is the smallest number of bits in which any 2 code words differ. Thus, the minimum distance of the BCD or the XS3 codes is 1, while that of the codes in Table 1.6 is 2. Clearly, a code is an error-detecting code if and only if its minimum distance is 2 or more. Error-correcting codes. For a code to be error-correcting, its minimum distance must be further increased. For example, consider the 3-bit code, which consists of only 2. Number systems and codes. Valid code words 000 and 111. If a single error occurs in the first code word, it could become 001, 010, or 100. The second code word could be changed by a single error to 110, 101, or 011. Note that in each case the invalid code words are different. Clearly, this code is error detecting since its minimum distance is 3. Moreover, if we assume that only a single error can occur, then this error can be located and corrected, since every error results in an invalid code word that can be associated with only one of the valid code words. Thus, the 2 code words 000 and 111 constitute an error-correcting code whose minimum distance is 3. In general, a code is said to be error-correcting if the correct code word can always be deduced from the erroneous word. In this section, we shall discuss a type of single error-correcting codes known as Hamming codes. If the minimum distance of a code is 3, then any single error changes a valid code word into an invalid one, which is distance 1 away from the original code word and distance 2 from any other valid code word. Therefore, in a code with minimum distance 3, any single error is correctable or any double error detectable. Similarly, a code whose minimum distance is 4 may be used for either single error correction and double error detection or triple error detection. The key to error correction is that it must be possible to detect and locate erroneous digits. If the location of an error has been determined, then, by complementing the erroneous digit, the message is corrected. The basic principles in constructing a Hamming error-correcting code are as follows. To each group of M information or message digits, K parity-checking digits, denoted P1, P2, Pk, are added to form an M plus K digit code. The location of each of the M plus K digits within a code word is assigned a decimal value. One starts by assigning a 1 to the most significant digit and M plus K to the least significant digit. Then K parity checks are performed on selected digits of each code word. The result of each parity check is recorded as 1 or 0, depending, respectively, on whether an error has or has not been detected. These parity checks make possible the development of a binary number, C1, C2, Ck, whose value is equal to the decimal value assigned to the location of the erroneous digit when an error occurs and is equal to 0 if no error occurs. This number is called the position or location number. The number k of digits in the position number must be large enough to describe the location of any of the m plus k possible single errors, and must in addition take on the value 0 to describe the no error condition. Consequently, k must satisfy the inequality 2k greater than or equal to m plus k plus 1. Thus, for example, if the original message is in BCD where M equals 4 then K equals 3 and at least 3 checking digits must be added to the BCD code. The resultant error-correcting code thus consists of 7 digits. In this case, if the position number is equal to 101, it means that an error has occurred in position 5. If, however, the position number is equal to 000, the message is correct. In order to be able to specify the checking digits by means of only message digits and independently of each other, they are placed in positions. 1.3 Error Detection and Correction Table 1.7 Position Numbers C1, C2, C3 Position Number Error Position C1, C2, C3 0 No error 0 0 0 1 0 0 1 2 0 1 0 3 0 1 1 4 1 0 0 5 1 0 1 6 1 1 0 7 1 1 1 1 2 4 2 K minus 1. Thus, if 4 and K 3, then the checking digits are placed equals the equals. M in positions 1, 2, and 4 while remaining positions contain the original BCD message bits. For example, in the code word 110, 0110, the checking digits in boldface are P1 equals 1, P2 equals 1, P3 equals 0, while the message digits are 0, 1, 1, 0, which correspond to decimal 6. We shall now show how the Hamming code is constructed by constructing the code for M equals 4 and K equals 3. As discussed above, the parity checking digits must be specified in such a way that, when an error occurs, the position number will take on the value assigned to the location of the erroneous digit. Table 1.7 lists the 7 error positions and the corresponding values of the position number. It is evident that if an error occurs in position 1, or 3, or 5, or 7, the least significant digit, i.e., C3, of the position number must be equal to 1. If the code is constructed so that in every code word the digits in positions 1, 3, 5, and 7 have even parity, then the occurrence of a single error in any of these positions will cause an odd parity. In such a case, the least significant digit of the position number is recorded as 1. If no error occurs among these digits, a parity check will show an even parity and the least significant digit of the position number is recorded as 0. From Table 1.7, we observe that an error in positions 2, 3, 6, or 7 should result in the recording of a 1 in the center of the position number. Hence, the code must be designed so that the digits in positions 2, 3, 6, and 7 have even parity. Again, if the parity check of these digits shows an odd parity, then the corresponding position number digit, i.e., C2, is set to 1. Otherwise, it is set to 0. Finally, if an error occurs in positions 4, 5, 6, or 7, then the most significant digit of the position number, i.e., C1, should be a 1. Therefore, if digits 4, 5, 6, and 7 are designed to have even parity, an error in any of these digits will be recorded as a 1 in the most significant digit of the position number. To summarize the situation regarding the checking digits pi, P1 is selected so as to establish even parity in positions 1, 3, 5, 7. P2 is selected so as to establish even parity in positions 2, 3, 6, 7. P3 is selected so as to establish even parity in positions 4, 5, 6, 7. Number Systems and Codes Table 1.8 Hamming code for BCD digit position and symbol decimal 1 2 3 4 5 6 7 digit P1 P2 M1 P3 M2 M3 M4 0 0 0 0 0 0 0 0 1 1 1 0 1 0 0 1 2 0 1 0 1 0 1 0 3 1 0 0 0 0 1 1 4 1 0 0 1 1 0 0 5 0 1 0 0 1 0 1 6 1 1 0 0 1 1 0 7 0 0 0 1 1 1 1 811000090011001. The code can now be constructed by adding the appropriate checking digits to the message digits. Consider, for example, the message 0100, i.e., decimal 4, as shown in the table below. Digit position 1, 2, 3, 4, 5, 6, 7. Digit symbol P1, P2, M1, P3, M2, M3, M4 original BCD message 0100 parity check in positions 1, 3, 5, 7 requires P1 equals 1. 10100 parity check in positions 2, 3, 6, 7 requires P2 equals 0. 100 parity check in positions 4, 5, 6, 7 requires P3 equals 1. 1001100 coded message 1001100. Thus, checking digit P1 is set equal to 1 so as to establish even parity in positions 1, 3, 5, and 7. Similarly, it is evident that P2 must be 0 and P3 must be 1, so that even parity is established, respectively, in positions 2, 3, 6, and 7, and 4, 5, 6, and 7. The Hamming code for the decimal digits coded in BCD is shown in Table 1.8. Error location and correction are performed for the Hamming code in the following manner. Suppose, for example, that the sequence 110-1001 is transmitted, owing to an error in the fifth position, the sequence 110-1101 is received. The location of the error can be determined by performing 3 parity checks as follows. Digit position, message received, 4-5-6-7 parity check, 2-3-6-7 parity check, 1-3-5-7 parity check, 111. 23410111056101711C101C2 equals 1 since parity is odd equals 0 since parity is even equals 1 since parity is odd. Thus, the position number formed as C1, C2, C3 is 101, which means that the location of the error is in position 5. To correct the error, the digit in position 5 is complemented and the correct message 110-1001 is obtained. Notes and references. It is easy to prove that the Hamming code constructed as shown above is a code whose distance is 3. Consider, for example, the case where the two original 4-bit code words differ in only one position, e.g., 1001 and 0001. Since each message digit appears in at least 2 parity checks, the parity checks that involve the digit in which the two code words differ will result in different parities and hence different checking digits will be added to the two words, making the distance between them equal to 3. For example, consider the two words below. Digit position, 1, 2, 3, 4, 5, 6, 7 digit symbol. P1, P2, M1, P3, M2, M3, M4. First word, 1001 second word, 0001 first word with parity bits, 001001 second word with parity bits, 110001. The two words differ in only M1, i.e., position 3. Parity checks 1-3-5-7 and 2-3-6-7 for these two words will give different results. Therefore, the parity checking digits P1 and P2 must be different for these words. Clearly, the foregoing argument is valid in the case where the original code words differ in 2 of the 4 positions. Thus, the Hamming code has a distance of 3. If the distance is increased to 4, by adding a parity bit to the code in Table 1.8 in such a way that all 8 digits have even parity, the code may be used for single error correction and double error detection in the following manner. Suppose that 2 errors occur, then the overall parity check is satisfied but the position number, determined as before from the first 7 digits, will indicate an error. Clearly, such a situation indicates the existence of a double error. The error positions, however, cannot be located. If only a single error occurs, the overall parity check will detect it. Now, if the position number is 0, then the error is in the last parity bit. Otherwise, it is in the position given by the position number. If all 4 parity checks indicate even parities, then the message is correct. For minimization, Chapter 44.1 Introduction Minimization of Switching Functions. A switching function can usually be represented by a number of expressions. Our aim in this chapter will be to develop procedures for obtaining a minimal expression for any such function after establishing some criteria for minimality. In the preceding chapter, we dealt with simplification of switching expressions by means of algebraic manipulations. The deficiency of this method is that it does not constitute an algorithm and is ineffective for expressions of even a small number of variables, e.g., 4 or 5. The methods to be introduced in this chapter partly overcome these limitations. The presented map method is very effective for the simplification by hand of expressions of up to 5 or 6 variables, while the tabulation procedure is suitable for machine computation and yields minimal expressions. Is to find our aim in simplifying a switching function f, x1, x2, xn, expression g, x1, x2, xn, which is equivalent to f and which minimizes some cost criteria. There are various criteria to determine minimal cost. The most common are 1. The minimum number of appearances of literals. Recall that a literal is a variable in complemented or uncomplemented form. 2. The minimum number of literals in a sum of products or product of sums expression. 3. The minimum number of terms in a sum of products expression, provided that there is no other such expression with the same number of terms and fewer literals. In subsequent discussions, we shall adopt the third criterion and restrict our attention to the sum of products form. Of course, dual results can be obtained by employing the product of sums form instead. Note that the expression 67. Minimization of switching functions is minimal according to criterion 3, although it may be written xy plus xc plus xy as xy plus c plus xy, which requires fewer literals. Consider the minimization of the function f, x, y, z, given below. A combination of the first and second product terms yields xc. Y plus y equals xc. Similarly, combinations of the second and third, fourth and fifth and sixth terms yield a reduced expression for f, x, z equals x plus y plus yz plus x plus y, yz xy, zyz xyz xy, zz z plus xz. This expression is said to be in an irredundant form, since any attempt to reduce it, either by deleting any of the 4 terms or by removing a literal, will yield an expression that is not equivalent to f. In general, a sum of products expression, from which no term or literal can be deleted without altering its logic value, is called an irredundant, or irreducible, expression. The above reduction procedure is not unique, and a different combination of terms may yield different reduced expressions. In fact, if we combine the first and second terms of f, the third and sixth, and the fourth and fifth, we obtain the expression f x z equals x plus xy plus y zyz. In a similar manner, by combining the first and fourth terms, the second and third, and the fifth and sixth, we obtain a third irredundant expression, f x z equals xy plus y zxz. While all three expressions are irredundant, only the latter two are minimal. Consequently, an irredundant expression is not necessarily minimal, nor is the minimal expression always unique. It is, therefore, desirable to develop procedures for generating the set of all minimal expressions so that the appropriate one may be selected according to other criteria, e.g., the distribution of gate loads, etc.
4.2 The map method.
The algebraic procedure of combining various terms and applying to them the rule AA plus AA equals A becomes very tedious as the number of terms and variables increases. The map method presented in this section and the tabulation procedure in section 4.4 provide systematic methods for combining terms and obtaining minimal expressions. Representation of functions. A Carnot map, hereafter usually referred to simply as a map, is actually a modified form of truth table in which the arrangement of combinations is. 4.2 The map method figure. 4.1 Carnot maps for XY, ZXY, Z3, and 4 variables. 0, 0, 0, 1, 11, 10, 0, 0, 0, 1, 11, 10, 1, 3, 0, 7, 2, 5, 46, 11, 1, 0, 0, 1, 1.
XY.
A. Location of minterms in A. B. Map for function f, x, y, z, 3-variable map. 2, 6, 7. Equals yz plus equals wx wx yz yz 0 0 0 1 11 10 0 0 0 1 11 10 1 5 13 9 0 3 2 4 7 6 12 15 14 8 11 10 11 1 1 1 1 0 0 0 0 0 1 0 1 11 11 10 10 C. Location of minterms in A. D. Map for function f, w, x, y, z, 4-variable map. 4, 5, 8, 12, 13, 14, 15 equals wx plus xy plus wyz equals. Particularly convenient. The maps for functions of 3 and 4 variables are shown in figure 4.1. The column headings are labeled with the 4 combinations of the 2 corresponding variables. The row headings correspond to the binary values of z in the 3-variable map and to the values of yz in the 4-variable map. Each n-variable map consists of 2 n cells, squares, representing all possible combinations of these variables. The decimal codes that correspond to these combinations are shown in figures 4.1a and c. We shall subsequently refer to particular cells by these decimal codes. The function value associated with the particular combination is entered in the corresponding cell. For example, the map of the function f, x, y, z equals 2, 6, 7 is shown in Fig. 4.1b, where the value 1 is entered in cells 2, 6, and 7. See figure 4.1a. A blank cell means that for the corresponding combination, the value of the function is 0. The minterm that corresponds to a particular cell is determined as in the truth table. The variable 11 appears in uncomplemented form in the product if it has value 1 in the corresponding cell, and in complemented form if it has value 0. For example, cell 6 in the 3-variable map corresponds to xyz, and in the 4-variable map it corresponds to wxyz. Fig. 4.1d shows the map for function f, w, x, y, z equals 4, 5, 8, 12, 13, 14, 15. The cyclic code used in listing the combinations as column and row headings is of particular importance. As a result of this coding, cells that have Akamonside correspond to combinations that differ by the value of just a single variable. In general, 2 cells that differ in just one variable value are said to. Minimization of switching functions. be adjacent and play a major role in the simplification process because they may be combined by means of the rule AA plus AA equals A, where A denotes a product of literals and A denotes a single literal. For the purpose of determining adjacencies, it is useful to regard the three-variable map as the surface of a cylinder formed by joining the left and right sides of the map. Similarly, the four-variable map is regarded as an open face of a torus, that is, the left and right sides of the map are joined, as are its top and bottom. This has the result, for example, that cell 8 is adjacent to cells 0 and 10 in addition to its obvious adjacency to cells 9 and 12. The product term corresponding to two adjacent cells for which the function has the value 1 is obtained by writing down the product of all those variables whose values are the same in the two cells, and deleting the variable which is complemented in one cell and uncomplemented in the other. For example, the term that corresponds to cells 2 and 6 of figure 4.1b is yz, since xyz plus xyz equals yz. For each minterm of n literals, there are n other minterms that have n-1 the literals in common with it, differing from it in just one literal. Utilizing geometrical properties of the map, it is easy to verify that in the three-variable map each cell is adjacent to three other cells, and in the four-variable map each cell is adjacent to four other cells. Simplification and minimization of functions. A collection of two M cells, each adjacent to M cells of the collection, is called a cube, and the cube is said to cover these cells. Each cube can be expressed by a product containing n minus m literals, where n is the number of variables on which the function depends. The m literals that are not contained in the product can be eliminated because each of their two m combinations appear in the product with the same factor. For example, the square array of four ones in figure 4.1d corresponds to plus z equals plus z wxy, zw xy wxy, zw xy xy, w zw w zw z xy. Similarly, the product expressing the linear array of four ones is wx, since the values of both w and x are the same in the four cells, while the value of yz is different in each cell. Now consider the function f defined by the map of figure 4.1b. We could express f as the sum of three minterms. However, observing that the map consists of two pairs of adjacent cells, we can express f as the sum of two product terms, f equals yz plus xy. The use of cell 6 in forming both cubes is justified by the idempotent law, cf. section 3.1. In this example, the corresponding algebraic manipulations. 4.2 The map method leading to the above result are x equals x plus f yz xyz xyz equals plus z yz xyz 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 xx equals xy yz xy zyz plus. In general, by the idempotent law, any cell may be included in as many cubes as desired. For example, the function f defined by the map of Fig. For point 1, d can be expressed as the sum of three products corresponding to the three cubes indicated on the map, i.e., equals plus xy plus f wx wyz. From the preceding discussion, we observe that a function f can be expressed as a sum of those product terms that correspond to the cubes necessary to cover all its one cells. The number of product terms in the expression for f is equal to the number of cubes, while the number of literals in each term is determined by the size of the corresponding cube. In order to obtain a minimal expression, we must cover all the one cells with the smallest number of cubes in such a way that each cube is as large as possible. Hence, a cube contained in a larger cube must never be selected. If there is more than one way of covering the map, i.e. its one cells, with the minimal number of cubes, we must select a covering that consists of larger cubes. Such a selection guarantees that the corresponding expression is indeed minimal and that no other expression containing the same number of terms, but fewer literals, exists. A cube contained in any combination of other cubes already selected in the covering of the map is redundant by virtue of the consensus theorem, equation 3.19. The foregoing discussion suggests the following rules for obtaining simple expressions for f.
1.
Start by covering with cubes those one cells that cannot be combined with any other one cell, and continue to those which have only a single adjacent one cell, and thus can form cubes of only two one cells. 2. Next, combine those one cells that yield cubes of 4, but are not part of any cube of 8 cells, and so on. 3. A minimal expression is one that corresponds to a collection of cubes that are as large and as few in number as possible, such that every one cell in the map of the function is covered by at least one cube. Example 2 irredundant expressions for f, w, x, y, z equals 0, 4, 5, 7, 8, 9, 13, 15 can be derived from the maps of Figure 4.2. The expression derived from Fig.
4,2 a i s f równa się x is plus xy plus wys plus xz.
Since none of the cubes is. Minimization of switching functions wx wx yz yz 0 0 0 1 11 10 0 0 0 1 11 10 0 0 1 1 1 1 1 1 1 0 1 11 10 1 0 0 0 1 11 10 11 1 1 1 1 1 1. A. F equals xyz plus wxy plus wyz plus xz. B. F equals wyz plus wxy plus xz is an irredundant expression. Unique minimal expression. Figure 4.22 irredundant expressions for f, w, x, y, z equals 0, 4, 5, 7, 8, 9, 13, 15. Contained either within a combination of other cubes or within a larger cube, this expression is irredundant. However, since it does not contain the smallest possible number of terms, it is not a minimal expression. The expression derived from the map of Fig. For point 2b, f equals wyz plus wxy plus xz is the unique minimal expression for f. There exist two more irredundant expressions for f, but neither of them is minimal. Example: the function fz, w, x, y equals 1, 5, 6, 7, 11, 12, 13, 15 has only one irredundant form as opposed to the preceding example. This unique minimal expression is derived from Fig. 4.3 and is found to be f equals wxy plus wyz plus wxy plus wyz. Note that the dotted cube xz of 4 ones becomes redundant if rule 1 is followed, since all its cells are covered by the other cubes. 0 0 0 1 11 10 wx yz 0 0 0 1 11 10 11 1 1 1 1 1 1 Figure 4.3 map for f equals wxy plus wyz plus wxy plus wyz. 4.2 The map method. Figure 4.4 Minimal wx sum of products and yz 0 0 0 1 11 10 0 0 0 1 11 10 product of sums forms 0 0 0 1 11 10 1 1 1 1 0 0 0 1 11 10 11 1 1 0 0 0 0 0 0 0 0 0 0 0 0. B. Map of f, x, y, z. A. Map of f, x, y, z equals 5, 6, 9, 10 equals 0, 1, 2, 3, 4, 7, 8, 11, 12, 13, 1, 4, 15 equals wxyz plus wxyz plus wxyz plus wxyz plus x równa się plus f plus x. So far, we have specified a switching function by combining the 1 cells. Clearly, it may equally well be specified by the 0 cells. In the latter case, the expression yields the complement f, whose ones are the zeros of f and vice versa. Determination of the minimal product of sums. The minimization of functions expressed as product of sums is the dual procedure if that just developed for the sum of products form. An immediate question arises as to whether the number of literals required in the minimal expressions of both forms is the same. Supposing that we have obtained a minimal sum of products expression for f, does this imply that the minimal product of sums expression will require at least as many literals? The answer to this question is negative, as is shown subsequently. Consider the function fz, w, x, y, equals 5, 6, 9, 10. From the cube shown in figure 4.4a, it is evident that no two 1 cells are adjacent. Thus, f cannot be reduced, and its minimal sum of products form consists of 16 literals in 4 minterms, fz equals z plus plus z plus, w, x, y, w x y w x y z w x, y w x y z. The minimal product of sums expression for a function f is defined in an analogous manner to the minimal sum of products. It consists of the product of a minimum number of some factors, provided that there is no other such product with the same number of factors and with fewer literals. The product of sums expression is obtained from the map in the same way as from the truth table. A variable corresponding to a 1 is complemented, and a variable corresponding to a 0 is uncomplemented. Cubes are formed of 0 cells instead of 1 cells and are selected in exactly the same manner as in the sum of products case. The minimal product of sums expression for f is derived from the map of Fig. 4.4b ie f równa się is vx plus w x y x w. Minimization of switching functions. This expression consists of only 8 literals as against 16 in the sum-off products form. Hence, if a minimal expression is sought, regardless of its form, both forms must be determined and the one with a smaller number of literals selected. Don't care combinations. So far, the functions considered have been completely specified for every combination of variables. There exist situations, however, where, while a function is to assume the value 1 for some combinations and the value 0 for others, it may assume either value for a number of combinations. Such situations may occur when the variables are not mutually independent. That is, dependency among the variables may preclude the occurrence of certain combinations, for which, consequently, the value of the function will not be specified. Combinations for which the value of the function is not specified are called don't-care combinations. The value of the function for such combinations is denoted by phi or d. In practice, when x1, x2, xn are variables designating the inputs to a switching circuit, and when f, x1, x2, xn designates its output. It often happens that for certain input combinations the value of the output is unspecified, either because these input combinations are invalid or because the precise value of the output is of no importance. Since each don't-care combination can be specified in either of two ways, i.e., 0 or 1, an incompletely specified function containing k don't-care combinations actually corresponds to a class of 2k distinct functions. Our task is thus to choose the function or functions having the minimal representation. When employing the map of an incompletely specified function, we assign the value 1 to selected don't-care combinations and the value 0 to others, in such a way as to increase the size of the selected cubes whenever possible. No cube containing only don't-care cells can be formed because it is not required that the function equal 1 for these combinations. Example: design a code converter that converts B seed messages into XS3 code. The converter has 4 input lines carrying signals labeled W, X, Y, and Z, and 4 output lines carrying signals F1, F2, F3, and F4. The inputs and outputs correspond, respectively, to BCD and XS3 coded messages. If the system operates properly, then the input combinations will correspond to the decimal values 0 through 9, while the remaining 6 combinations, 10 through 15, will never occur and thus may be regarded as don't-care combinations. The code converter is designed by considering each output function separately. The truth table specifying the codes is shown in Figure 4.5a and the resulting output functions in Figure 4.5b. The simplification of output functions is accomplished by use of the corresponding maps, as shown in Figure 4.6. Don't care combinations are 75. 4.2 The map method decimal number WBCD inputs X, Y, Z, XS 3 outputs F, 3 F, 2 F, 1 0 1 2 3 4 5 6 7 8 9 0 0 0 0 0 0 0 0 1 1 0 0 0 0 1 1 1 1 0 0 0 0 1 1 0 0 1 1 0 0 0 1 0 1 0 1 0 1 0 1 0 0 0 0 0 1 1 1 1 1 0 1 1 1 1 0 0 0 0 1 1 0 0 1 1 0 0 1 1 0 1 0 1 0 1 0 1 0 1 0. A truth table for BCD and XS. 3 codes F1, 0, 2, 4, 6, 8, plus phi, 10, 11, 12, 13, 14, 15, equals F2 equals 3, 4, 7, 8 plus 0, phi, 10, 11, 12, 13, 14, 15, F3 equals 2, 3, 4, 9 plus 1, phi, 10, 11, 12, 13, 14, 15, F4 equals 6, 7, 8, 9 plus 5, phi, 10, 11, 12, 13, 14, 15. B. Output functions. Figure 4.5 Specifications of a code converter. WX YZ YZ 0 0 0 111 10 0 0 0 111 10 0 0 1 1 1 1 0 111 10 1 0 0 0 111 10 1 1 1 1 1 F1 map F2 map WX YZ YZ 0 0 0 111 10 0 0 0 111 10 0 0 1 1 1 1 0 111 10 1 0 0 0 1 11 10 1 1 1 1 1 F3 map F4 map. Figure 4.6 maps for a BCD to XS 3 code converter. Minimization of switching functions. Considered and specified in each function regardless of the specification in other functions. Generally, the specification is done in such a way as to increase the size of the cubes in the map without making it necessary to select more cubes than would be necessary if fewer don't cares were made ones. The minimal functions derived from the maps are F1 equals Z, F2 equals Y, Z plus YZ, F3 equals XY plus XZ plus XYZ, F4 equals W plus XY plus XZ. A gate network 1 realizing the code translator is shown in Figure 4.7. Note that if, owing to a malfunction in the message, an invalid input combination occurs, then the output of the code converter will also be erroneous. Z F1YZ F2YZX, YX F3ZXYZ. XWYF4XC Figure 4.7 ABCD to XS 3 code converter. A switching circuit in which a set of n input variables determines the values of 2 or more outputs is called a multi-output circuit. The above code converter is a 4-output circuit. 1. Any gate network that realizes a sum of products or a product of sums expression is called a 2-level realization, since it consists of one level of AND, or, gates driving a second level or AND gate. Thus, the longest path through which any input signal must pass until it reaches the output consists of 2 gates. A measure of the complexity of a network is either the overall number of gates or the total number of gate inputs. For example, the network of Figure 4.7 consists of 10 gates and 23 gate inputs. 4.2 The map method. Figure 4.85 variable map with the locations of minterms. The 5-variable map 0 0 0 0 0 1 0 11 0 10 VWX YZ 110 billion 111 million 101,100 2, 6, 14, 10, 1, 0, 3, 4, 5, 7, 12, 13, 15, 8, 9, 11, 25, 24, 27, 26, 28, 29, 31, 30, 20, 21, 23, 22, 16, 17, 19, 18, 0, 0, 0, 1, 11, 10. The minimization procedure described so far with respect to functions of 3 or 4 variables can be extended to the case of 5 or 6 variables. For functions of 7 or more variables, the map is very large, and its value as an effective tool in the minimization procedure decreases, since it becomes very difficult to keep track of adjacencies. A 5-variable map contains 25 is equal to 32 cells, as shown in Figure 4.8. Each cell, in addition to being adjacent to 4 other cells, can be combined with a 5th cell on the other side of the center symmetry line. Thus, cell 9 in the map of Fig. 4.8 is adjacent to and therefore may be combined with cell 25, cell 15 is adjacent to 31, 4 to 20, and so on. Example with the aid of a map. Minimize the function f v z w x y equals 1, 2, 6, 7, 9, 13, 14, 15, 17, 22, 23, 25, 29, 30, 31. From the cube shown in Figure 4.9, we obtain the minimal sum of products expression. F, V, Z równa się x plus xy plus x, wx z v w y z 110 biliony 111 miliardy 101 miliony 100 tysiące 001 011 010 vwx y z 1 1111 11 1 1 1 1 1 1 1 stycznia 2000 roku 1 listopada 2010 roku FIK 4 września map for f, v, x, z równa się x is plus wx z plus xy plus v w y z. Minimization of switching functions. The extension of the map to 6 variables is accomplished in a similar manner. The map is a square consisting of 64 cells, where each cell is adjacent to 6 other cells. The actual construction of the map, the determination of the appropriate row and column headings, and the locations of the midterms are left to the reader as an exercise. For point 3 minimal functions and their properties. In section 4.1, we observe that there exists a distinction between irredundant and minimal expressions, and that neither is necessarily unique. We shall now investigate the properties of these expressions and determine the characteristics of the product terms contained in a minimal sum of products expression. Prime implicants. A switching function f, x1, x2, xn, is said to cover another function, this action being denoted by f superset of or equal to g, if f assumes the value a 1 in every row of the truth g, x1, x2, xn, 1 whenever g does. Thus, if f covers g, then it has table in which g has a 1. If f covers g, and at the same time g covers f, then f and g are equivalent. Let f be a switching function and be a x1, x2, xn, h, x1, x2, xn product of literals. If f covers h, then h is said to imply f. H is said to be an implicant of f. The implication is often denoted by hf. Example, if f and h, then f covers h and h implies f. Equals plus equals wx, yz, wxy. Definition 4.1. A prime implicant p of a function f is a product term covered by f such that the deletion of any literal from p results in a new product that is not covered by f. Alternatively stated, p is a prime implicant if and only if p implies f, but does not imply any product with fewer literals that in turn also implies f. The set of all prime implicants of f will be denoted by p. Example, a prime implicant of is y, since it is equals x, y plus x, z plus yf. F, zx covered by f and neither x nor y alone implies. Theorem 4.1. Every irredundant sum of products equivalent to f is a union of prime implicants of f. Proof: let f asterisk operator be an irredundant sum of products expression equivalent to f, and suppose that f asterisk operator contains a product term q that is not a prime implicant. Since q is not a prime implicant, it is possible to replace it with another product that consists of fewer literals. Hence, F contains redundant literals, which contradicts the initial assumption. Diamond suit. For point 3, minimal functions and their properties. The next task is to generate the set of all prime implicants of F, and from this set to select those prime implicants whose union yields a minimal expression for F. Suppose that F is given in a canonical sum of products form. Then, by applying the combining theorem AA plus AA equals A to a pair of minterms, we obtain a product that implies F. Repeated applications of this theorem to all pairs of terms that differ in the value of just one variable yield a set of products, each of which implies F. A product that cannot be combined with any other product to yield a still smaller product, i.e., one with fewer literals, is a prime implicant of F. Thus, our first step in the determination of the minimal expression is a systematic combination of terms. The second step, that of selecting the minimal set of prime implicants, is in general more complicated, as will be demonstrated in the next section. On the map for F, an irreducible product corresponds to a cube that is not contained in any larger cube. Consequently, the set P of all prime implicants can be obtained by writing down the products corresponding to all the cubes that are not contained in any larger cubes. Example: consider the map of FC, W, X, Y, equals 0, 4, 5, 7, 8, 9, 13, 15, given in figure 4.2. The set of all prime implicants of F is P equals XC, WYZ, WXY, XYZ, WXY, WYZ. Note that XYZ is not a prime implicant since it implies XC. Deriving minimal expressions. An inspection of the maps in Fig. 4.2 reveals that the prime implicant XC must be contained in any irredundant expression equivalent to F, since it is the only product that covers the combinations 7 and 15. However, any other one cell is covered by 2 prime implicants and, consequently, none of them is essential for the specification of an irredundant expression. A prime implicant P of a function f is said to be an essential prime implicant if it covers at least one minterm of f that is not covered by any other prime implicant. Since every minterm of f must be covered by an expression for f, all essential prime implicants must be contained in any irredundant expression for this function. Example: the prime implicants of the function fz, w, x, y, equals 4, 5, 8, 12, 13, 14, 15 are all essential, as demonstrated by the map of figure 4.1d. Minimization of switching functions. Example: the map for the function f, x, z, y, equals 0, 2, 3, 4, 5, 7 is shown in Fig. 4.10. It is known as a cyclic prime implicant map, since no prime implicant is essential. All prime implicants have the same size, and every cell is covered by exactly 2 prime implicants. The reader can verify by means of this map the results obtained in an algebraic manner in section 4.1. XYZ 0, 0, 0, 1, 11, 10, 1, 1, 1, 1, 1, 1, 0, 1. Figure 4.10a map for the function f, x, y, z, equals 0, 2, 3, 4, 5, 7. Since every minterm covered by a non-essential prime implicant is covered by at least 2 prime implicants, any non-essential prime implicant is covered by the sum of some prime implicants. For example, the prime implicant wxy of the function whose map is shown in figure 4.2 is covered by the sum of the prime implicants xc and wyz. An essential prime implicant, however, is not covered by any such sum. When simplifying expressions by means of a map, we start by selecting essential prime implicants, if any. This is accomplished by first forming maximal cubes of those ones that can be combined to form only one cube. Any other cube whose ones are contained in one or more of these cubes corresponds to a redundant term and need not be considered further. We thus arrive at the following conclusion. The set of all essential prime implicants must be contained in any irredundant sum of products expression. while any prime implicant covered by the sum of the essential prime implicants must not be contained in an irredundant expression. For example, the prime implicant xc of function f of figure 4.3 is covered by the sum of 4 essential prime implicants and, therefore, must not be contained in any irredundant expression for f. We can thus summarize the procedure for obtaining a minimal sum of products expression for a function f. 1. Determine all essential prime implicants and include them in the minimal expression. 2. Remove from the list of prime implicants all those that are covered by the essential prime implicants. 3. If the set derived in step 1 covers all the minterms of f, then it is the unique minimal expression. Otherwise, select additional prime implicants such that 4.4 The tabulation procedure for the determination of prime implicants f is covered completely and such that the total number and size of the prime implicants thus added are minimal. The execution of step 3 is not always straightforward. While in most cases with only a small number of variables, this execution can be done by inspecting the map in more complicated cases and when the number of variables is large. A more systematic method is needed. The prime implicant chart presented in the next section is a possible tool aiding the search for a minimal expression. 4.4 The tabulation procedure for the determination of prime implicants. The Carnot map method described in the preceding sections is very useful for functions of up to 6 variables. In order to manipulate functions of a larger number of variables, a more systematic procedure, preferably one that can be carried out by a computer, is necessary. The tabulation procedure, known also as the Quine-McCluskey method of reduction, satisfies the above requirements. It is suitable for hand computation and is also easily programmable. The binary representation. The fundamental idea on which this procedure is based is that repeated applications of the combining theorem AA plus AA equals A to all adjacent pairs of terms yield the set of all prime implicants, from which a minimal sum may be selected. The technique will be introduced by minimizing the function z equals 0, 1, 8, 9 equals plus z plus plus f1 w x y w x y z w x y w x y z w x y z. The first two and last two terms of f1 can be combined to yield z y z z y z z equals plus plus w x y.
f1 x x w x x.
These two terms can be combined in turn and we obtain z y w equals x plus f1 w x y w y. In the first step we obtained, for each of the two pairs of adjacent terms, consisting of 4 literals per term, one term that consists of 3 literals. In the second step, these two terms were combined again and reduced to a single 2-literal product. A similar result could have been obtained by initially combining the first and third and the second and fourth terms in the original function. However, no combination of the first and fourth or the second and third terms is possible because they are not adjacent. Therefore, our first task is minimization of switching functions to determine, in a simple and systematic way, which terms can or cannot be combined and to carry out all possible such combinations. 2 k-variable terms can be combined into a single k-1 variable term if and only if they have in common k-1 identical literals and differ in just a single literal. The combined term consists of the product of the k-1 identical literals, while the variable, which is uncomplemented in one term and complemented in the other, is deleted. Thus, the terms wxyz and wxyz can be combined to wxy, while wxyz and wxyz cannot be combined, since they differ in 2 variables, i.e., w and z. If we consider the binary representation of the minterms, we observe that the necessary and sufficient condition for 2 minterms to be combinable is that their binary representations differ in just one position. For example, the representations for wxyz and wxyz are 0001 and 1001, respectively. The combined term is denoted -001, where the dash indicates that variable w has been absorbed and the combined term is xyz. The terms wxyz and wxyz, however, cannot be combined since their binary representations 0001 and 1000 differ in two positions, i.e., in the first and fourth digits. For the binary representations of two minterms to be different in just one position, it is necessary that their numbers of ones differ by exactly 1. Consequently, to facilitate the combination process, the minterms are arranged in groups according to the number of ones in their binary representation. With the following steps, the procedure becomes systematic. 1. Arrange all minterms in groups such that all terms in the same group have the same number of ones in their binary representation. Start with the least number of ones and continue with groups of increasing numbers of ones. The number of ones in a term is called the index of that term. 2. Compare every term of the lowest index group with each term in the successive group. Whenever possible, combine the two terms being compared by means of the combining theorem AA plus AA equals A. Repeat this by comparing each term in a group of index I with every term in the group of index I plus 1 until all possible applications of the combining theorem have been exhausted. Two terms from adjacent groups are combinable if their binary representations differ by just a single digit in the same position. The combined term consists of the original fixed representation, the different digit being replaced by a dash, hyphen symbol. A check mark is placed next to every term which has been combined with at least one term. Note that each term may be combined with several terms, but only a single check is required. 3. Now compare the terms generated in step 2. In the same fashion, a new term is generated by combining two terms that differ by only a single one and whose dashes are in the same position. The process continues until no further combinations are possible. The remaining unchecked terms constitute the set of prime implicants of the function. 4.4 The tabulation procedure for the determination of prime implicants. Figure 4.11 Determination of the Step 1, Step 2, Step 3. Set of prime implicants for the function f2, w, x, y, z equals 0, 1, 2, 5, 7, 8, 9, 10. Vx 00, 1, 1, 0, 1 do 0, 0, 0, 1, 8, 9, 0, 2, 8, 10, 5, 7, 13 i 15 setnych 1, 5, 9 i 13 setnych uz ADC B01010011001100. WXYZ 10101 110 to 0100 010 to 0010 0 to 0000 to 010 21 51 92 108 98 105 75 130 811 to 1 1111 0113 157 159 1300 01113 15 WXYZ 0 0000001811005010910017011131111. The entire procedure is, actually, a mechanized process for combining and reducing all adjacent pairs of terms. The unchecked terms are the prime implicants of f, since each implies f and is not covered by any other term with fewer literals. We shall illustrate the procedure by applying it to the function z f2 w x y equals 0, 1, 2, 5, 7, 8, 9, 10, 13, 15. The left-hand part of figure 4.11, corresponding to the application of step 1, consists of all minterms, arranged in groups of increasing indices. The reduced terms, after the first application of step 2, are given in the center part. For example, the combination of the terms 0000 and 0001 is recorded by writing 000 in its first row, where the dash indicates that variable z is redundant. The terms 0000 and 0001 in the left-hand part of the figure are now checked off. The same rule is applied repeatedly until all combinable terms are recorded in the center part. The entire procedure is now repeated for the groups just formed in the center part of the figure. Again, only adjacent groups need be compared, and a new term is generated whenever two terms that differ in only one position and have their dashes in the same position are found. This procedure guarantees that the two combined terms actually consist of the same variables, that is, the same variable was deleted from both terms in the previous step. The new terms are recorded in the right-hand part of the figure, while the appropriate terms are checked off. For example, the term 000 can be combined with 100 to form -00, which is recorded in the first row. While recording the terms in the right-hand part of the figure, we observe that each term is generated in two ways. For example, the term -00 is generated in the preceding manner as well as by combining -000 and -001. Clearly it is. Minimization of switching functions. Figure 4.12 illustration of the two wx ways of generating a term. YZ 000 111 10 000 111 10 1 1 1 1 1 111 100 minus 0000 minus 000 0101 minus 001 11 000 minus 11 10 10. Sufficient to record it once, but checks must be placed next to each of the four terms 000 100 -000 and -001. The cause of this phenomenon is that every four-cell cube can be formed by combining two adjacent two-cell cubes in two ways, as illustrated for the preceding example in Figure 4.12. The terms recorded in the right-hand part of Figure 4.11 and labeled A, B, C, and D cannot be combined with any other term and, therefore, form the set of prime implicants of F2. From this set, we must now select a minimal subset whose union is equivalent to F2. This is accomplished by means of the prime implicant chart presented in the section 4.5. The decimal representation. The tabulation procedure can be simplified further by adopting the decimal code for the minterms rather than their binary representation. Two minterms can be combined only if they differ by a power of 2, that is, only if the difference between their decimal codes is 2i. The combined term consists of the same literals as the minterms with the exception of the variable whose weight is 2i, which is deleted. For example, if we consider the function f1, w, x, y, z equals 0, 1, 8, 9, the minterms 1 and 9 differ by 23 is equal to 8, and consequently the variable w, whose weight is 8, is deleted. This combining process, which is recorded by placing the weight of the redundant variable in parentheses, e.g., 1, 9, 8, is simply a numerical way of describing the algebraic manipulation wx, y, z plus wx, y, z equals xyz. Similarly, the combination of the minterms 0 and 8 is written as 0, 8, 8. The condition that the decimal codes of two combinable terms must differ by a power of 2 is necessary, but not sufficient. Two terms whose codes differ by a power of 2 but which have the same index cannot be combined, since they differ by more than one variable. Similarly, if a term with a smaller index has a higher decimal value than another term whose index is higher, then the two terms cannot be combined although they may differ by a power of 2. For example, the terms 9 and 7 in Figure 4.11, whose indices are 2 and 3, respectively, cannot be combined since they differ in the values of 3 variables, except for the 4.4 the tabulation procedure for the determination of prime implicants 8, 8.
Fig.
4.13 tabulation procedure 1, 2, 1812, 13FG, 1611, 17H, 16, 17, 19, 21, 23, 24, 2, 17, 19, 25, 27, 2, 13, 15, 29, 31, 2, 16, B, 19, 23, 27, 31, 4, 8, 21, 23, 29, 31, 2, 8, 17, 21, 25, 29, 4. For F3, V, W, X, Y, Z, using 12 decimal notation. The tables are derived in the order A-D. 17, 2, 17, 19, 18, 4, 17, 21, 21, 19, 13, 24, 20, 2, 1, 1, 1, 8, 17, 25, 18, 19, 20, 21, 24, 25, 13, 15, 8, 4, 16, 19, 27, 19, 23, 13, 29, D, 31, 29, 27, 23, 15, 25, 23, 31, 15, 31, 25, 29, 25, 27, 21, 29, 21, 23, 8, 16, 4, 2, 8, 2, CEA, 25, 27, 29, 31, 2, 4, C, 17, 19, 21, 23, 25, 27, 29, 31, 2, 4, 8, A, D, 29, 31, 27, 31, 2, 4, B. Above phenomenon, the tabulation procedure using the decimal representation is completely analogous to that using the binary representation. The tabulation procedure can easily handle the case of don't care combinations. During the process of generating the set of prime implicants, don't care combinations are regarded as true combinations. That is, combinations for which the function assumes value 1. This, in effect, increases to the maximum the number of possible prime implicants. The don't care terms are, however, not considered in the next step, that of selecting a minimal set of prime implicants, as will be shown in the following section. The tabulation procedure for generating the set P of prime implicants for the function f3, v, w, x, y, z, 13, 15, 17, 18, 19, 20, 21, 23, 25, 27, 29, 31, 1, 2, 12, 24, equals plus phi, is shown in figure 4.13. This set consists of 8 prime implicants, denoted A through H, i.e., equals Z. P of VZ, WXC, VWXY, 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 WXYZ, WXY. 86 Minimization of switching functions. Figure 4.14 prime implicant chart for F2, W, X, Y, Z of figure 4.11. A equals XY, B equals XC, C equals YZ, D equals XC 0, 1, 2, 5, 7, 8, 9, 10, 13, 15. The selection of the prime implicants to be used in the minimal sum is accomplished with the aid of the prime implicant chart presented in the next section. For point 5, the prime implicant chart. The prime implicant chart displays pictorially the covering relationships between the prime implicants and minterms of a function. It consists of an array of U columns and V rows, where U and V designate the number of minterms for which the function takes on the value 1 and the number of prime implicants, respectively. The entries of the ith row in the chart consist of times S placed at its intersections with columns corresponding to minterms covered by the ith prime implicant. For example, the prime implicant chart of F2, W, X, Y, Z equals 0, 1, 2, 5, 7, 8, 9, 10, 13, 15 is shown in figure 4.14. It consists of 10 columns, corresponding to the minterms of F2, and 4 rows which correspond to the prime implicants A, B, C, and D generated in figure 4.11. Row C contains 4 times S at the intersections with columns 1, 5, 9, and 13, because these minterms are covered by the prime implicant C. A row is said to cover the columns in which it has times S. The problem now is to select a minimal subset of prime implicants such that Each column contains at least 1 times in the rows corresponding to the selected subset, and the total number of literals in the prime implicant selected is as small as possible. These requirements guarantee that the union of the selected prime implicants is indeed equivalent to the original function f, and that no other expression containing fewer literals and equivalent to f can be found. Essential rows. If any column contains just a single times, then the prime implicant corresponding to the row in which this times appears is essential and consequently must be included in any irredundant expression for f. The times is circled, and a check mark is placed next to the essential prime implicant. The row that corresponds to an essential prime implicant is referred to as an essential row. Once an essential prime implicant has been selected, all the minterms it covers are checked off. For example, essential prime implicant B covers, in addition to columns 2 and 4.5, the prime implicant chart. 10, columns 0 and 8. Consequently, columns 0, 2, 8, and 10 are checked off. If, after all essential prime implicants and their corresponding columns have been checked, the entire function is covered, i.e., every column is checked off, then the union of all essential prime implicants yields the minimal expression. If this is not the case, then additional prime implicants are necessary. The 2 essential prime implicants B and D of F2 cover all the minterms except 1 and 9. These minterms may be covered by either prime implicant A or C, and since both are expressed with the same number of literals, we obtain 2 minimal expressions for F2, namely Z equals x plus xz plus xf2, w, x, y, zy, and z equals x plus xz plus yf2, w, x, y, zz. Don't care combinations. Don't care minterms need not be listed as column headings in the prime implicant chart, since they do not have to be covered by the minimal expression. By not listing them, we actually leave the specification of the don't care terms open. That is, if a minimal expression contains a prime implicant derived from a don't care combination, this amounts to specifying that combination as 1. Otherwise, the don't care combination is, in effect, assigned the value 0. The prime implicant chart thus yields a minimal expression of a function which covers all the specified minterms. The prime implicant chart for the function f3, v, w, x, y, z, 13, 15, 17, 18, 19, 20, 21, 23, 25, 27, 29, 31, 1, 2, 12, 24, equals plus phi, whose prime implicants have been computed in Figure 4.13, is shown in Figure 4.15. Figure 4.15, the prime implicant 13, 15, 17, 18, 19, 20, 21, 23, 25, 27, 29, 31 chart for F3, V, W, X, Y, Z of A equals VZ. Figure 4.13. B equals WXC, C equals VWXY, D equals VWXY, E equals VWXY, H equals WXYZ, G equals WXYZ. F equals VWXY. Minimization of switching functions. The selection of non-essential prime implicants is facilitated by the initial listing of prime implicants in a descending order according to the number of minterms they cover. Thus, prime implicants that are located in a higher group in the chart are expressed with fewer literals than those located in a lower group. A horizontal line across the chart separates one group from the other. The essential prime implicants in the chart of Figure 4.15 are A, B, and D. They cover all the specified minterms, with the exception of 18. This last minterm can be covered by either of prime implicants E and G, and, since both have the same number of literals, 2 minimal expressions can be found, namely Z equals VZ plus F3, V, W, X, Y, WXZ, VW, XY, VW, XY, and Z equals VZ plus F3, V, W, X, Y, WXZ, VW, XY, W, XYZ. Determination of the set of all irredundant expressions. So far, We have been able to determine minimal sum of products expressions by inspecting the prime implicant chart. In more complex cases, however, the inspection process becomes prohibitively time-consuming and different techniques are in order. As an illustration, consider the minimization of the function z f4 v w x y equals 0, 1, 3, 4, 7, 13, 15, 19, 20, 22, 23, 29, 31. The corresponding prime implicant chart is shown in Figure 4.16a, where the essential prime implicants and all minterms covered by them have been checked off. While every irredundant expression must contain the prime implicants a and c, none may contain b, since b covers only terms already covered by a and c. The reduced chart, which results after the removal of rows a, b, and c and all columns covered by them, is shown in Figure 4.16b. Every column of the reduced chart contains 2 times s, and our task is to select a minimal number of additional prime implicants so as to cover the entire function. Utilizing the techniques of propositional calculus, we associate a 2-valued variable with each remaining prime implicants. The truth value of such a variable is 1 if the corresponding prime implicant is included in the irredundant expression and is 0 if it is not. Define a prime implicant function p to be equal to 1 if each column is covered by at least one of the chosen prime implicants and 0 if it is not. For example, column 0 can be covered by either row h or row
I.
Consequently, either h or I must be included in any irredundant expression. Similarly, either g or I must also be included, since only they have times s in column 1. Deriving the appropriate expressions from the remaining columns. 4.5 The prime implicant chart figure 4.16 determination of all irredundant expressions for F4 equals 0, 1, 3, 4, 7, 13, 15, 19, 20, 22, 23, 29, 31. A, B, C. D equals F equals 0, 1, 3, 4, 7, 13, 15, 19, 20, 22, 23, 29, 31 WXC XYZ WYZ VWXY WXYZ VWXC H equals G equals I equals VWYZ VWXC VWXY A. Prime implicant chart 014-2022 DHGFEI B. Reduced prime implicant chart. Of Figure 4.16b, we obtain the expression for P, HI, GI, FF, DE equals plus PH, E which can also be written as a sum of products.
Uguale più PE F di FE GH di FGH.
From this
expression for P we find that at least 3 rows are needed to cover the reduced chart, for example rows E, H, and I, or rows E, F, and I. There are 5 irredundant expressions for F4, corresponding to the 5 product terms for which P assumes the value 1. Also, since all the prime implicants that correspond to the rows of the reduced chart have the same number of literals, there are only 4 minimal expressions, corresponding to the first 4 terms in P. Each of these minimal expressions is obtained by forming the sum of the essential prime implicants A and C and a minimal number of prime implicants necessary to set P equal 1. Thus we have Z equals plus VF4, V, W, X, Y, WXZ WYZ VWXZ VWYZ VWXY, F4, V, W, X, Y, WXZ WYZ VWXZ WXYZ WXY, F4, V, W, X, Y. Z equals WXZ plus WYZ plus VWXY plus WXYZ plus VWXY, F4, V, W, X, Y, Z equals WXZ plus WYZ plus VWXZ plus VWXZ plus VWYZ. Reduction of the chart minimization of switching functions. The foregoing method for determining the irredundant sets of prime implicants can be applied directly to the prime implicant chart, instead of to the reduced chart. However, the prime implicant function will be, in most cases, considerably simpler if first the essential rows and columns covered by them are removed. Note that in deciding whether a product term in P corresponds to a minimal expression, two factors must be considered: the number of prime implicants and the number of literals in each such prime implicant. In general, prime implicant charts are not as simple as the examples we have given, and more elaborate techniques for manipulating them are required. Whenever our aim is limited to finding just one minimal expression rather than all minimal expressions, the selection of prime implicants may be considerably simplified. Consider the minimization of the function f5, v, w, x, y, z, equals 1, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 25, 26, 27. Its prime implicant chart is shown in Fig 4.17a, where the essential prime implicants a, b, j, and k and all minterms covered by them have been checked off. The reduced chart, which is obtained by removing the essential rows and the columns covered by them, is shown in Fig 4.17b. Although none of the rows in the reduced chart is essential, some of them may be removed. For example, row H has n times in column 19, while row G has times S in columns 19 and 11. Since both prime implicants G and H belong to the same group in the chart, i.e., both are expressed with the same number of literals, the removal of row H cannot prevent us from finding at least one minimal expression. In other words, two expressions that are identical except that one contains G while the other contains H will have the same number of literals. And since G covers the minterm covered by H, it can replace H in every expression for F5 without affecting its logic value or its number of literals. Note that the converse is not true, since the removal of row G may leave column 11 without any times in a row whose corresponding prime implicant must be contained in the minimal expression. A row U of a prime implicant chart is said to dominate another row V of that chart if U covers every column covered by V. Generalizing the preceding arguments, we conclude that if row U dominates row V and the prime implicant corresponding to row U does not have more literals than the prime implicant corresponding to row V, then row V can be deleted from the chart. Thus, row I of Fig 4.17b can be deleted because it is dominated by row G and, similarly, rows D and F are removed because they are dominated by rows C and E, respectively. The final reduced chart is shown in Fig 4.17c. It contains 3. 4.5 The prime implicant chart Fig 4.17 minimization of equals 1 3 4 5 6 7 10 11 12 13 14 15 18 19 20 21 22 23 25 26 27 F5 1 3 4 5 6 7 10 11 12 13 14 15 18 19 20 21 22, A equals WX. B equals VX, C equals VXY, D equals VWY, F equals VWY, E equals WXY 23, 25, 26, 27. G equals XYZ, H equals WYZ, I equals VYZ, J equals VWZ, K equals VWXZ, A, prime implicant chart. 10 11 18 19 26 10 11 18 26 19 C. C G F E D H I E G, C, final chart. B, reduced prime implicant chart. Rows, of which 2, C and E, must be included in the minimal expression, since only they cover columns 18 and 10, respectively. Clearly, the inclusion of C and E is also sufficient, since they cover all the columns not covered by the essential prime implicants. The minimal expression for F5 thus consists of the prime implicants A, B, J, K, C, and E, i.e., Z, equals x plus v x plus z y plus f5, v, w, x, y, w v w v w x v x w x y. Prime implicant charts can also be reduced by removing certain columns. Consider, for example, columns 10 and 11 in Fig 4.17b. In order to cover column 10, either row E or F must be selected, whereby column 11 will also automatically be covered since it has times S in rows E and F. The converse is not true, since column 11 can also be covered by row G, but this will not cover column 10. A column I in a prime implicant chart is said to dominate another column J of that chart if I has n times in every row in which J has n times. Clearly, any minimal expression derived from a chart which contains both columns I and J can be derived from a chart which contains only the dominated column. Hence, if column I dominates column J, then column I can be deleted from. Minimization of switching functions Fig 4.18 minimization of f6 equals 0, 1, 5, 7, 8, 10, 14, 15, by the branching method. The branching method wxyza equals wxy00011 10 0 1 5 7 8 10 1415 00. B equals WYZC equals WXZ11111110 10 1 D equals XYZE equals WXYG equals WXZF equals WYZH equals XYZ, A, cyclic map. 5 7 8 10 14, B, cyclic prime implicant chart. 15 1 5 7 10 14 15. C, reduced chart after, D, reduced chart after selection of row A selection of row H. The chart without affecting the search for a minimal expression. In fact, the removal of dominating columns does not prevent us from finding all minimal expressions. Note that, when reducing columns the dominating ones are removed, while of the rows the dominated ones are deleted. The removal of dominated rows and dominating columns may alternate a number of times, that is, we may start by removing dominated rows and dominating columns. This in turn may create new dominated rows that can be removed, and so on. It may happen that a prime implicant chart has no essential prime implicants, dominated rows, or dominating columns. Whenever this happens, a different approach must be taken, called the branching method. Consider, for example, the function z, f6, w, x, y, equals 0, 1, 5, 7, 8, 10, 14, 15. Whose map, which is cyclic, is given in Fig 4.18a. 8 prime implicants of equal size are derived from the map and are shown in the chart of Fig 4.18b, BFEDCGHAEDCBFG. 4.6 Map entered variables where each prime implicant covers two minterms and each minterm is covered by two prime implicants. Such a chart is called a cyclic prime implicant chart. In order to find a minimal expression for f6, it is necessary to make an arbitrary selection of one row and then apply the above reduction procedure. Consider, for example, column 0 in Fig 4.18b. It can be covered by either row A or H. Consequently, one of these rows must be included in any minimal expression. If row A is arbitrarily chosen, the chart of Fig 4.18c results. In this chart row B is dominated by row C and row H is dominated by row G. After removal of these dominated rows, we find that
rows C and G must be selected, since only they cover columns 5 and 8, respectively. This selection, in turn, implies the inclusion of row E in the expression for f6, i.e., z equals plus f6, w, x, y, wxy, wxc, wxy, wxc. The entire process must now be repeated for row H as the initial selection. The removal of this row results in the chart of Figure 4.18d. This chart is again reduced by removing the dominated rows A and G and including the prime implicants B, D, and F in the expression for F6, Z, equals Z plus X F6, W, X, Y, W, Y, X, Y, Z, W, Y, Z, Y, Z. Since the two expressions for F6 have the same number of literals, both are minimal. In general, there is no guarantee that the initial arbitrary selection will result. In a minimal expression, it is, therefore, necessary to repeat the process for each row that could be substituted for the initially selected one. Although the prime implicant chart of a function whose map is cyclic is itself always cyclic, it is possible to encounter cyclic charts in the process of reducing a prime implicant chart that corresponds to a non-cyclic map. Moreover, a cyclic chart may result while applying the branching process and reducing another cyclic chart. Whenever such a situation occurs, another arbitrary row selection must be made and all alternative expressions must be obtained, such that a minimal one may be selected. 4.6 Map-entered variables. The Carnot map can be made a considerably more powerful tool if the variables themselves are entered into the map cells. In the preceding utilization of the map, the function value associated with the particular combination was entered in the corresponding cell, that is, a value of 1, 0, or don't care is entered into a cell. In practice, it often happens that, for a particular combination, the function value is neither a constant, i.e., 0 or 1, nor a don't care, but rather depends on the value of some other external variable. For example, the entry in cell XYZ equals 0, 10 in the map of figure 4.19 is A. This implies that the value minimization of switching functions figure 4.19 deriving expressions from map-entered variables 10 A B C A B X Y Z 0 1 0 0 0 1 11 10 A initial map XY Z Z 0 0 0 1 11 10 0 0 0 1 11 10 0 110 0 0 1 0 0 0 0 0 0 0 1 1 B map for A, C, map for B. Of the function f for this combination is a function of the variable a, that is, f is equal to 1 if a equals 1 and f is equal to 0 if equals 0. Similarly, the value of f corresponding to the input combination xyz equals 0, 0, 1 depends on the value of variable b, while the value of f corresponding to input combination xyz equals 101 depends on the value of b. A map of the type shown in figure 4.19a, in which some cell entries are external variables, is said to have map-entered variables. A major advantage of such a map is that with an n-variable map, i.e., a map containing two n cells, we can specify functions of more than n variables. The three-variable map shown in Fig. 4.19a, for example, specifies a function of 6 variables x, y, z, and a, b, c. The product term that corresponds to a cell-entered variable is equal to the product of the variable entered into the cell and the combination that identifies the cell. For example, the product corresponding to cell 010 is xyz, and the product corresponding to cell 101 is bxyz. The procedure for covering such a map and generating a simple expression for the corresponding function can be summarized as follows. 1. Treat all map-entered variables as zeros and find a minimal expression for the resulting map. 2. To cover the first map-entered variable, say A, treat all other map-entered variables as zeros and treat all ones as don't cares. Find a minimal cover for the resulting map. 3. Repeat step 2 for each map-entered variable. Note that, in this context, a variable and its complement are treated as distinct variables, i.e., B and B in figure 4.19 are distinct variables. 4.7 Heuristic to level circuit minimization. Following this procedure, we can find a minimal expression corresponding to the map in figure 4.19a. From step 1, it is evident that the one in the map is covered by the cube yz. Step 2 for variable a is illustrated in figure 4.19b. Clearly, the corresponding term is I. Similarly, from figure 4.19c, we obtain the term for b, namely bxc. The terms for b and c are found in a similar manner, and the entire function is given by equals yz plus I plus z plus b plus f bx x c c x y z. 4.7 Heuristic Two-Level Circuit Minimization. Part 3 Finite-state Machines. Warning: Empty page. Chapter 9 Introduction to Synchronous Sequential Circuits and Iterative Networks. In Part 2 we considered combinational switching circuits in which the output values are functions of only the current circuit input values. In most digital systems, however, additional circuits are necessary that are capable of storing information and data and also of performing some logical or mathematical operations upon this data. The output values of these circuits at any given time are functions of external input values as well as of the stored information at that time. Such circuits are called sequential circuits. Point 1. A finite-state machine, or finite automaton, is an abstract model describing the synchronous sequential machine and its spatial counterpart, the iterative network. It is the basis for the understanding and development of the various computation structures discussed in Part 3 of this book. The behavior, capabilities, limitations, and structure of finite-state machines are studied in Chapters 12 through 16, while Chapters 9 and 10 are devoted to the synthesis of these machines. Chapter 11 is concerned with asynchronous sequential circuits. 9.1 Sequential circuits. Introductory example. In our daily activities, we all encounter the use of various sequential circuits. The elevator control which remembers to let us out before it picks up people coming into elevator, traffic light systems on our roads, trains, and subways. The lock on a safe that not only remembers the combination numbers, but also their sequence. All these are examples of sequential circuits in action. Before deriving the basic model and general synthesis procedures, we shall investigate the properties of a simple sequential circuit. 1. Conventionally, the term sequential machine refers to the abstract model that represents the actual sequential circuit. In many cases, however, these terms are used interchangeably. 265. Introduction to Synchronous Sequential Circuits and Iterative Networks. Figure 9.1 Block diagram of a serial binary adder. The state table serial adder 001011x100011Z. Consider the serial binary adder, whose block diagram is shown in Figure 9.1. It is a synchronous circuit with two inputs, x1 and x2, carrying the two binary numbers to be added and one output, z, which represents the sum. Fixed-length sequences of zeros and ones are fed to the inputs and obtained at the outputs. The addition is to be performed serially. The least significant digits of numbers x1 and x2 arrive at the corresponding input terminals at time t1. A unit time later, the next to least significant digits arrive at the input terminals, and so on. The time interval between the arrival of two consecutive input digits is determined by the frequency of the circuit's clock. We shall assume that the delay within the combinational circuit is small with respect to the clock period, which is the inverse of the clock frequency, and as a consequence, the sum digit arrives at the z terminal soon after the arrival of the corresponding input digits at the input terminals. We shall denote by X and Z the input and output sequences, respectively, and by X and Z the input and output symbols at a specified point in time. We may often want to emphasize the precise time at which the input or output value occurs. In such cases, the notation XTI, Z, TI will be used. Consider the following addition of two binary numbers, T5, T4, T3, T2, T10, 1100 equals X10, 1110 equals X2 plus 11010 equals Z. An examination of the correlation between the input values and the required output value reveals the basic difference between a combinational circuit and the serial binary adder. While in a combinational circuit, the output value at time Ti is defined uniquely by the input values at Ti, in the serial adder different output values are required for identical input conditions. For example, at T1 and T5 the input values are X1, X2 equals 0, 0, but the required output values are Z equals 0 and Z equals 1, respectively. Similarly, at T3 and T4 the input values are X1, X2 equals 11 while the desired output values are 0 and 1, respectively. It is, therefore, evident that the output value of the serial adder cannot be specified merely in terms of the external input values, and so different design procedures must be employed. Following the rules of elementary binary arithmetic, it is evident that the output value at time Ti is a function of the input values X1 and X2 at that time and of the carry that was generated at Ti minus 1. This carry which may have either X2. 9.1 Sequential circuits. Introductory example table 9.1 state table for a serial binary adder NS. ZPS X1 X2 equals 0 0 0 1 11 10 AA 0 A 1 B 0 A 1 B A 1 B 0 B 1 B 0. Of the two values 0 or 1, in turn depends on the input values at Ti minus 1 and on the able to preserve carry generated at Ti minus 2 and so on. Hence the adder must be information regarding its input values from the time it is set into operation up to time Ti. However, since the starting time may be long past, it is impossible to preserve the whole history of input values. We therefore seek a different relation between the input values X1, Ti, and X2, Ti, and the output value Z, Ti, as follows. In the case of the serial adder, we can distinguish two classes of past input histories, one resulting in the production of a carry 0 and the other in producing a carry 1. These classes will be called the internal states, or simply states, of the adder. By memorizing the value of the carry, the adder actually shows some trace of its past input values, at least to the extent of their influence on the response to current input values. Let A designate the state of the adder at Ti if a carry 0 is generated at Ti minus 1, and let B designate the state of the adder at Ti if a carry 1 is generated at Ti minus 1. We refer to the state of the adder at the time when the current input values are applied to it as its present state, PS, and the state to which the adder goes. As a result of the new, not necessarily different, carry value, as the next state, NS. The output value Z, Ti, is a function of the input values X1, Ti, and X2, Ti, and the state of the adder at time Ti. The next state of the adder depends only on the current input values and on the present state. A convenient way of describing the behavior of the serial adder is by means of a state table, as shown in Table 9.1. Each row of the state table corresponds to a state of the adder, and each column to a particular combination of the external input values X1 and X2. Each entry of the table denotes the state to which a transition is made and the output value associated with this transition. For example, if the adder is in state A, i.e., the current carry is 0, and it receives the input combination X1, X2 equals 11, then it will go to state B, which corresponds to carry 1, and produce an output value Z equals 0. The remaining entries of the table can be verified in a straightforward manner, and since the table contains 8 entries, corresponding to the 8 combinations of states and input values, it completely specifies the serial adder. It is often convenient to use a directed graph as a counterpart to the state table. Such a graph, shown in Figure 9.2, is known as the state diagram or state graph. The vertices and directed arcs of the graph correspond to the states of the adder and to its state transitions, respectively. The labels of the directed. Introduction to Synchronous Sequential Circuits and Iterative Networks. Figure 9.2 State Diagram for a Serial Adder. The state assignment 11/000/0AB010/101/010/011/1. Arcs specify the input values and the corresponding output values, e.g., 10 to 0 represents the condition x1 equals 1, x2 equals 0, and z equals 0. Clearly, both the state diagram and state table provide the same information regarding the operation of the adder, and one can be obtained directly from the other. While in many cases these representations are equally suitable, in some applications one may be more convenient than the other. In order to implement the serial adder, it is necessary to use some device capable of storing the information regarding the presence or absence of a carry. Such a device must have two distinct states, such that each can be assigned to represent a state of the adder. A number of such devices exist, among which is the delay element, which may simply consist of a D flip-flop, to be described subsequently. The capability of the delay element to store information is a result of the fact that it takes a finite amount of time for input signal Y to reach its output Y. The length of the delay is usually equal to the interval between two successive clock pulses. For convenience, we will assume that this delay is 1 time unit long. The state of the delay element is specified by the value of its output Y, which may assume either of two values, namely Y equals 0 or Y equals 1. Since the current input value Y of the delay is equal to its next output value, the input value is referred to as the next state of the delay, that is, Yt equals Yt plus 1. If we assign the states of the delay to those of the adder in such a way that Y equals 0 is assigned to A and Y equals 1 to B, the value of Y at Ti will correspond to the value of the carry generated at Ti minus 1. The process of assigning the states of a physical device to the states of the serial adder is known as state assignment, or secondary state assignment. The output value Y is referred to as the state variable or secondary variable to distinguish it from the external primary input variables. The state assignment is completed by modifying the entries of the state table to correspond to the states of Y in accordance with the selected state assignment. The resulting table is given in Table 9.2, where the next state and output entries have been separated into two sections. The entries of the next state table define the necessary state transitions of the adder and thus specify the next value of the output, Yt plus 1, of the delay. In addition, since Yt equals Yt plus 1, these entries also specify the input values to the delay at time t required to achieve the 9.2 The finite state model. Basic definitions. Table 9.2 The transition and output tables for a serial binary adder. Next state Y output Z x1, x2 x1, x2 y0 0 0, 111 10 0 0 0, 111 10 0 0 0, 1 0 0 1 0 1 1 0 1 1. 1 1 0 1 0 x1 Figure 9.3 Serial binary adder. X2 full adder Z, YC0 delay Y. Desired state transitions. Thus, the next state part of Table 9.2, which is called the transition table, serves also to specify the required excitation of the delay. The output part of Table 9.2, which is identical to that of Table 9.1, specifies the output value Z for every combination of x1, x2, and y. Consequently, using the map method, the following logic equations result: equals Z equals x plus plus plus, y times 1 times 2 times 1 y times 2y, 1 times 2y times 1 times 2y plus plus x1 x2 y times 1 times 2y. These equations are clearly identical to those obtained in section 5.4 for the carry and some functions of the full adder. The addition is accomplished by retransmitting the carry C0 of the full adder through the delay Y into the full adder's input, as shown in figure 9.3. Note that a delay whose input is Y is generally referred to as delay Y. 9.2 The finite-state model, basic definitions. The behavior of a finite-state machine is described as a sequence of events that occur at discrete instants designated t equals 1, 2, 3, etc. Suppose that a machine M has been receiving input signals and has been responding by producing output signals. If now, at time t, we were to apply an input signal xt to M, then its response c, t, would depend on xt as well as on the past input signals to M. Also, since a given machine M might have an infinite variety of possible histories, it would need an infinite capacity for storing them. Since it is impossible to implement machines that have infinite shall concentrate on those machines whose past histories can affect their future behavior in only a finite number of ways. For example, suppose Introduction to Synchronous Sequential Circuits and Iterative Networks Figure 9.4 Circuit Representation X1 of a synchronous, sequential XL machine. Combinacional Logic Z1 y 1 y 1 YK y 2 y 2 ZM. Memory devices. That the serial binary adder of the previous section has been receiving input signals. Its response to the signals at t is a function only of these signals and the value of the carry generated at t-1. Thus, although the adder may have a large number of possible input histories, they may be grouped into two classes, those resulting in a carry 1 and those resulting in a carry 0 at t. We shall study machines that can distinguish among a finite number of classes of input histories and shall refer to these classes as the internal states of the machine. Every finite-state machine, therefore, contains a finite number of memory devices, which store the information regarding the past input history. Note that although we are restricting our attention to machines that have finite storage capacity, no bound has been set on the duration for which a particular input value may affect the future behavior of the machine. A discussion of this subject is deferred to Chapter 14. Synchronous sequential machines. In general, a synchronous sequential machine is represented schematically by the circuit of Figure 9.4. The circuit has a finite number L of input terminals. The signals entering the circuit via these terminals constitute a set x1, x2, xl input variables, where each xj for all j may take on one of the two possible values 0 or 1. An ordered L tuple of zeros and ones is an input configuration, alternatively, input symbol, pattern, or vector. The set I of P equals 2L distinct input patterns is called the input alphabet, and each configuration is referred to as a symbol of the alphabet. Thus, the input alphabet is given by I equals I1, I2, IP. For example, if a machine has two input variables x1 and x2, then its input alphabet consists of four symbols, or configurations. That is, I equals 0, 0, 0, 1, 11, 10. Similarly, the circuit has a finite number M of output terminals which define the set Z1, Z2, Zm of output variables, where each Zj for all j is a. 9.2 The finite-state model, basic definitions. Binary variable. An ordered M tuple of zeros and ones is an output configuration, alternatively, output symbol, pattern, or vector. The set O of Q equals 2M ordered M tuples is called the output alphabet and is given by equals O, O1, O2, OQ, where each output configuration is a symbol of the output alphabet. The signal value at the output of each memory element is referred to as the state variable, and a Y1, Y2, YK constitutes the set of state variables. The combination of values at the outputs of the K memory elements Y1, Y2, YK defines the present internal state, or state, of the machine. The set S of N equals 2K K-tuples constitutes the entire set of states of the machine, where S equals S1, S2, Sn, the external input values x1, x2, xl, and the values of the state variables y1, y2, Yk are supplied to the combinational circuit, which in turn produces the output values Z1, Z2, Zm, and the Y1, Y2, Yk values. The values of the Ys, which appear at the outputs of the combinational circuit at time t, are identical to the values of the state variables at t+1 and, therefore, they define the next state of the machine, i.e., the state that the machine will assume next. Synchronization is achieved by means of clock pulses feeding the memory devices. Specification of machine behavior. The relationships between the input symbol, present state, output symbol, and next state are described by either a state table or a state diagram. A state table has p columns, one for each input symbol, and n rows, one for each state. For each combination of input symbol and present state, the corresponding entry specifies the output symbol that will be generated and the next state to which the machine will go. Although in practice every machine of the type shown in Figure 9.4 has two L input symbols and two K states, some of them may be theoretically unnecessary. In other words, theoretically a machine may have any number p of input symbols and n of states. However, in practice, when realizing such a machine, the actual circuit will have L equals log 2p input terminals and K equals log 2n memory elements, where G is the smallest integer larger than or equal to G. To each state of the machine there corresponds a vertex in the state diagram, cf. Figure 9.2. From each vertex emanate p-directed arcs, corresponding to the state transitions caused by the various input symbols. Each directed arc is labeled by the input symbol that causes the transition and by the output symbol that is to be generated. Since both the state table and state diagram contain the same information, the choice between the two representations is a matter of convenience, as mentioned above. Both have the advantage of being Introduction to synchronous sequential circuits and iterative networks precise, unambiguous, and thus more suitable for describing the operation of a sequential machine than any verbal description. The succession of states through which a sequential machine passes and the output sequence which it produces in response to a known input sequence are specified uniquely by the state diagram, or table, and the initial state, where by the initial state we refer to the state of the machine prior to the application of the input sequence. The state of the machine after the application of the input sequence is called the final state. 9.3 Memory elements and their excitation functions. In discussing the basic model for synchronous sequential machines, we showed that a state table, or diagram, completely specifies the behavior of the machine. In order to design a circuit that operates according to the specifications of a given table, it is necessary first to select a number of memory elements, each of which is a device with two distinct states and is capable of storing a binary digit. The states of these elements are next assigned to the states of the machine, a process known as state assignment. A transition table is derived from a state table by the replacement of each next state entry with a corresponding state of memory elements. A transition table thus specifies for every combination of input values and state variables the next state of the memory elements, which is given by Y1, Y2, Yk. To generate these Ys, the memory elements must be supplied with appropriate input values. The switching functions, which describe the effect of the circuit inputs x1, x2, xl and state variables y1, y2, yk on the memory element inputs, are called excitation functions. These functions are derived from an excitation table, whose entries are the values of the memory element inputs. In section 9.1, we described the delay element as a memory device. Its storage capability is due to the fact that it takes a finite time for the signal to propagate through it. In practice, the most widely used memory element is the flip-flop, which is made up of latches. Set reset or SR latch. The set reset SR latch has two inputs, S and R, and two outputs, Y and Y, often denoted as the 1 and 0 outputs or Q and Q outputs, respectively. A block diagram representing an SR latch is shown in Figure 9.5a. Such latches are easily implemented with cross-coupled NOR or NAND gates, as shown in Figures 9.5b and 9.5c, respectively. The latch has two states, defined by y1 and y0. The output y is equals that s are the complement of y. The latch possesses the property it remains in one state indefinitely until it is directed by an input signal to do otherwise. A signal. 9.3 Memory elements and their excitation functions. Table 9.3 Excitation characteristics of the SR latch y, t, s, t, r, t, y, t plus 1, b 0 0 0 0 0 0 1 0 0 1 1, 0 1 0 1 1 1 0 1 1 1 1, 1 0 1 0 1 0 0 1. Figure 9.5 The SR latch. A RS equals 0.
B, T más 1, igual a I, T, más RS10 y SR, A, block diagram. RSS.
Fig 9.5 The SR latch. 1. Fig 9.5 The SR latch. A Rs equals 0. By, T plus 1, equals Y, T, plus RS10 Y SRY, A, block diagram. RSSYYRYY, B, NOR latch.
Figure 9.5 The SR latch. A RS equals 0.
B, T más 1, igual a I, T, más RS10 y SR, A, block diagram. RSSII, RII, B, NOR latch.
C. NAND latch. At the input S sets the latch to the one state, i.e., it sets Y equals 1. A signal at the of the SR latch R input R resets it to the 0 state. The excitation characteristics given in Table 9.3. If both R and S are excited simultaneously, the operation of the latch becomes unpredictable. Consequently, the requirement that the product RS equals 0 must be imposed to ensure that the two invalid combinations in Table 9.3 will never occur. The excitation requirements of the SR latch are summarized in Table 9.4, in which a dash denotes a situation where the value of the input is a don't care, since it does not affect the output value. In practice, a clocked or synchronous version of the SR latch is generalized. In this version, shown in Fig. 9.6, state changes can occur only in synchronization with the pulses from an electronic clock. To ensure proper operation, restrictions must be placed on the length of the clock pulses and on the frequency of the input changes so that the circuit will change state no more than once for each clock pulse. The synchronization of the S and R inputs with the clock is accomplished in Figure 9.6b by AND gating them before they enter the latch inputs. Introduction to Synchronous Sequential Circuits and Iterative Networks. Figure 9.6 Clocked SR latch. Figure 9.7 Trigger or T latch. Trigger or T latch. Table 9.4 Excitation requirements for the SR latch. Required value change in Y from to SR000 to 01101001111 to 0 RYY, SSYY, C clock R, A block diagram. B. Logic diagram.
T10I, clock TSR10I, A, block.
Required value change in Y from to SR000 to 01101001111 to 0 RYY SSYY C clock R, A, block diagram. B, logic diagram. T10YY clock TSR10YY, A, block diagram. SR, B, deriving the T latch from the clocked SR latch. 10. To simplify the logic
diagrams in subsequent sections, we will often ignore the clock, but it is important to note that in all synchronous circuits, the clock is implicit whether shown or not. The block diagram of the trigger, T, latch is shown in Figure 9.7a. The T latch has one input denoted T and two outputs denoted Y and Y. It has two distinct states defined by the logic value of Y, namely, the latch is in the 1 state when Y equals 1 and in the 0 state when Y equals 0. The output Y is the complement of Y. As in the case of the SR latch, The T-latch remains in one state indefinitely until it is directed by an input signal to do otherwise. A value 1 applied to its input triggers the latch, and it changes state. The terminal characteristics of the T-latch are summarized in Table 9.5. The next state function y, t plus 1, can be expressed in terms of the present state and 9.3 memory elements and their excitation functions. Table 9.5 excitation requirements for the T-latch change in y required from to value T0000111011110 figure 9.8, the JK latch. SRYY clock C10JK10YJY. B. Constructing the JK latch from the clocked SR latch. K. A. Block diagram. Input as follows. Y, t plus 1, t, y, t, equals t plus ty, t.
Tie circle plus.
A clocked T-latch can be realized by cross-coupling a clocked latch, as SR shown in Figure 9.7b. The clock in Fig. 9.6b is replaced by an and combination of the input T and a clock. If non-clocked operation is desired, the clock and AND gate in Figure 9.7b may be removed and T applied directly to the latch. In the clocked realization, if the value of the output y is 1, then the reset input value is 1. The latch will now change state to y equals 0 when Tc equals 1, that is, when the values of T and the clock are both 1. Similarly, when y equals 0, the set input value is 1, and the latch will change state to y equals 1 when Tc equals 1. The JK latch. The latch has the characteristics of both the and T latches. Inputs J, JK, SR, and K, like S and R, set and reset the latch, respectively. The combination J equals K equals 1 is permitted. When it occurs, the latch acts like a trigger and switches to its complement state. That is, if y equals 1, it switches to y equals 0, and vice versa. The block diagram and excitation requirements for the JK latch are shown in Figure 9.8a and Table 9.6, respectively. Introduction to Synchronous Sequential Circuits and Iterative Networks. Table 9.6 excitation requirements for the JK latch change in y from to required value JK 00110101010D. Figure 9.9 the D latch. 10YY D clock JK YYC10 A. Block diagram. B. Transforming the JK latch to a D latch. One possible realization of a clocked JK latch can be obtained clocked SR latch in the way shown in Figure 9.8b. The D latch. The block diagram and a possible realization of the D latch are shown in Figure 9.9. The next state of this device is equal to its present excitation. Hence, it is characterized by the equation y t plus 1 equals d t. This latch clearly behaves like the delay element discussed in the preceding sections and, consequently, its excitation requirements are specified by the transition table. Clock timing and the master-slave flip-flop. A clocked latch is characterized by the fact that it changes states only in synchronization with the clock pulse. Moreover, it changes state only once during each occurrence of a clock pulse. A sequential circuit operating under these restrictions is said to be a synchronous sequential circuit. The duration of the clock pulse is usually determined by the circuit delays and signal propagation time through the latches. In fact, the clock pulse must be long enough to allow the latch to change state and, at the same time, it must be short enough that the latch will not change state twice due to the same excitation. 9.3 Memory elements and their excitation functions. Figure 9.10 Excitation of a JK latch within a sequential circuit. YYJK clock combinational logic 1-0. Figure 9.11 Master-slave SR flip-flop.
Clock. SRI 10 SR 10 minutos.
In general, referring to the sequential circuit model of Fig. 9.4, the outputs of a latch, which serves as a memory element, are inserted into a combinational circuit, which, in turn, generates the excitation functions for that latch, as illustrated in Fig. 9.10. The length of the clock pulse, must be such that it will allow the latch to generate the Ys but will not be present when the values of the Ys have propagated through the combinational circuit. This fine-tuning of the length of the clock pulse is difficult to accomplish. To overcome this, another type of synchronous memory element called a master-slave flip-flop can be used. This flip-flop eliminates the timing problems associated with the feedback loop by essentially isolating the inputs of the flip-flop from its outputs. A master-slave SR flip-flop, shown in Figure 9.11, is constructed of two reset latches connected in series, with their clock inputs driven in a complementary manner. The first latch, called the master, can change state only when the clock is at 1, while the second latch, called the slave, can change state only when the clock is at 0. A change in excitation causes a change of state in the master latch. During that period, the slave latch maintains its previous state and serves as a buffer between the master and the next stage. When the clock changes from 1 to 0, the state of the master latch is frozen while the slave latch is enabled and changes its state to that of the master latch. The new state of the slave then determines the state of the entire master-slave flip-flop. Since the master-slave SR flip-flop still suffers from the drawback that both its inputs cannot simultaneously be 1, it can be converted to a master-slave JK flip-flop to avoid this problem. As shown in Figure 9.12a. Note the similarity to the JK latch shown in Figure 9.8b. The only difference is that the SR latch has been replaced by a master-slave SR flip-flop. Thus, when a master-slave JK flip-flop is substituted for the JK latch in Figure 9.10, the inputs of the combinational circuit do not change when the clock is at 1. When the clock is at 0, the Ys. Introduction to Synchronous Sequential Circuits and Iterative Networks, Figure 9.12 Master-Slave Flip-Flops. Figure 9.13 Master-Slave JK flip-flop with set and clear inputs. SR Master, Slave 10 JK DYY JK, YY10 JK Master, Slave. A. Master-Slave JK flip-flop. B. Master-Slave D flip-flop. Set JK YY master-slave clock clear. Change and, consequently, the output of the combinational circuit changes, but this cannot affect the state of the master latch. In practice, a master-slave flip-flop has 3 regular inputs, namely J, K, or S, R, and the clock, and 2 additional inputs called direct, set, and direct, clear, as shown in Figure 9.13. These latter inputs are added to the slave flip-flop and they override the regular input signals and clock. They are used either to set the slave output to 1 by applying 0 to the set input and 1 to the clear input, or to clear the slave output to 0 by applying complementary values to the set and clear inputs. It is not allowable to assign zeros to both the set and clear inputs simultaneously. If we assign both of them 1s, however, the circuit returns to the normal clocked master-slave operation. Such external inputs are very useful, for example, in the design of counters, where it may be necessary to reset a counter to a pre-specified count, or in the design of shift registers, to which must be cleared before the start of certain computations. Both master-slave and flip-flop suffer from the problem of 1's SR-JK catching and 0's catching. This arises from the fact that the master latch is transparent when the clock is high. Consider the JK flip-flop shown in Figure 9.12a. When the output of the slave latch is at 0 and the J input has a static 0 hazard, a transient glitch to 1, after the clock has gone high. Then the master latch catches this set condition and its output attains the value 1. It then too a shift register consists of a number of cascaded flip-flops. 9.3 Memory elements and their excitation functions. Figure 9.14a Negative edge-triggered D flip-flop.
Clock RSIID.
Passes this 1 to the slave latch when the clock goes low. This leads to 1's catching. Similarly, when the output of the slave latch is at 1 and the K input has a static 0 hazard after the clock has gone high, then the master latch catches this reset condition and its output attains the value 0, which is then passed on to the slave latch when the clock goes low. This leads to 0's catching. To avoid the above problems, a popular solution is to use a master-slave D flip-flop, as shown in Figure 9.12b. Note again the similarity to the D latch shown in Figure 9.9b. Now, even if a static hazard were to occur at the D input when the clock is high, the output of the master latch would revert to its old value when the glitch goes away. The master-slave T flip-flop can be obtained analogously by replacing the SR latch in Figure 9.7b with master and slave SR latches. Another type of flip-flop called an edge-triggered flip-flop yields a more efficient implementation in terms of the number of gates than master-slave flip-flops and hence is popular. This is discussed next. Edge-triggered flip-flop. A positive, negative, edge-triggered D flip-flop stores the value available on the D input when the clock makes a 0-1-1-0 transition. Any change at the D input after the clock has made a transition does not have any effect on the value stored in the flip-flop. Consider the negative edge-triggered D flip-flop shown in Figure 9.14. A positive edge-triggered flip-flop can be obtained simply by using the complement of the clock. It consists of 3 latches. When the clock is high, the output of the bottommost, topmost, NOR gate is at DD, whereas the S and R inputs of the output latch are both at 0, causing it to hold the previous value. When the clock goes low, the value from the bottommost, topmost, NOR gate gets transferred as D to the S, R input of the output latch. Thus, the output latch stores the value of D. If there is a change in the value of the D input of the Introduction to Synchronous Sequential Circuits and Iterative Networks. Flip-flop after the clock has made its transition. The output of the bottommost NOR gate attains the value 0, since its 2 inputs must have complementary values. However, it can be seen that this cannot change the SR inputs of the output latch. The excitation characteristics and requirements presented earlier for the various types of latch are also applicable to the corresponding flip-flops. In the subsequent discussion, we shall synthesize sequential circuits using flip-flops. To simplify the resulting tables and circuits, the clock is generally not shown. However, as mentioned before, it is implicit in all synchronous circuits. 9.4 Synthesis of synchronous sequential circuits. We have seen a synthesis procedure in section 9.1 for a serial binary adder using a delay as the memory element. In this section, we shall develop a general method for designing sequential circuits using various types of memory elements and apply this method to the design of some commonly used circuits. The main steps in the method are summarized as follows. 1. From a word description of the problem, form a state table or a state diagram that specifies the circuit behavior. 2. Check this table to determine whether it contains any redundant states. The notion of a redundant state will be defined in Chapter 10, where we shall also present methods for detecting and eliminating such states. The state tables in this section do not contain any redundant states. 3. Select a state assignment and determine the type of memory elements to be used. 4. Derive the transition and output tables. 5. Derive an excitation table and obtain the excitation and output functions from their respective tables. 6. Draw a circuit diagram. In effect, in Step 5 we are converting a less familiar problem, that of sequential circuit synthesis, into a more familiar problem, that of combinational circuit synthesis. Since the construction of the excitation table is actually equivalent to the construction of a set of maps, from which the derivation of the excitation functions is straightforward. The sequence detector. We wish to design a one-input, one-output sequence detector that produces an output value 1 every time the sequence 0101 is detected and an output value 0 at all other times. For example, if the input sequence is 010101, then the corresponding output sequence is 000101. In designing the sequence detector, 9.4 Synthesis of synchronous sequential circuits. Table 9.7 State table for a sequence detector NS. Z0 1x equals x equals PS 0 AB, A 0 BB, 0 C, 0 CD, 0 A, 0 DB, 0 C, 1 Figure 9.15 state diagram for a 1/0. A, B, C, D 0/0/0/0/0/0/0/0/0/0/0 sequence 0101 detector. We may find it more convenient to start the synthesis procedure by constructing the state diagram of the machine. At time t1, the machine is assumed to be in the initial state, designated arbitrarily as A. While in this state, the machine can receive input values 0 or 1. For each of these input values, an arc is drawn originating in state A and terminating in the appropriate next state, as shown in Figure 9.15. The arc labeled 1/0 forms a self-loop around state A, since the machine does not initiate the sequence detection process until it receives a 0 input value. The input value 0 indicates a possible start of the sequence to be detected and, therefore, an arc labeled 0/0 leads from state A to B. When the machine is in state B, a 1 input value takes it to state C, while a 0 input value leaves it in the same state. If, when the machine is in state C, it receives a 1 input value, its last 2 input values are 11 and, since this input sequence cannot be completed in any way to yield 0101, the machine is directed back to its initial state. The machine arrives at state D after having received an input sequence whose last 3 symbols are 010. An additional 1 input value produces a 1 output value and causes a transition from state D to C, which is the state corresponding to input sequences whose last 2 symbols are 01. A 0 input value, applied to the machine when in state D, causes a transition to B because the last 0 symbol may be the prefix of 0101. The state table corresponding to the diagram of Figure 9.15 is given in Table 9.7. The input and output symbols are denoted by X and Z, respectively. 2 state variables with 22 is equal to 4 states are needed for the representation of the 4 states of the sequence detector. If we select 2 delay elements, Y1 and Y2, as memory devices and choose the state assignment shown in the left-hand block of Table 9.8, we obtain the transition and output tables in the center and Introduction to Synchronous Sequential Circuits and Iterative Networks Table 9.8 Transition and Output Tables Y1 Y2 Z Y1 Y2 X equals 0 X equals 1 X equals 0 X equals 1 A B C D 0 0 0 1 11 10 0 1 0 1 10 0 1 0 0 11 0 0 11 0 0 0 0 0001 Figure 9.16 Output and Excitation Maps.
XXX y 1 y 2 y 1 y 2 y 1 y 2 0 1 0 1 0 1 1 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0 1 0 1 0 1 11 11 11 10 10 10 A Z map.
B Y1 map. C Y2 map. Right-hand blocks of Table 9.8. The entries of the transition table specify, for each combination of present state and input symbol, the values that the outputs of the delays should assume next. However, since the next values of the delays are equal to their present excitation, the transition table entries in effect specify the required excitation of the delay elements. Consequently, whenever delay elements are used as memory devices, the transition and excitation tables are identical. The output table is, actually, a 3-variable map in which the value of Z is specified for every combination of X, Y1, and Y2, as shown in Figure 9.16a. The excitation table consists of 2 distinct 3-variable maps, corresponding to the excitation functions for Y1 and Y2. Entries for the map of Y1, Y2 are given by the left-hand, right-hand, entries of the second block of Table 9.8. The logic equations, derived from the maps of Fig.
9.16. For the output and excitation functions are z igual a x, y1 y 2, y 1 igual a x, y 1 y 2 más y 2 igual a y 1 y más x y más y x, y1 y 2 x, y1 y 2, 2 1 más 1 y 2.
The implementation of these equations yields the sequence detector shown in Figure 9.17. The reader may have observed that the state assignment employed in Table 9.8 is not the only possible one. In general, different state assignments. 9.4 Synthesis of Synchronous Sequential Circuits Table 9.9 A Second Assignment Y1 Y2 Z Y1 Y2 X equals 0 X equals 1 X equals 0 X equals 1 A B C D 0 0 0 1 10 11 0 1 0 1 11 0 1 0 0 10 0 0 10 0 0 0 0 0 0 0 1. Figure 9.17 Logic diagram of a sequence detector.
X1 y 1 de y 2 y 2 de.
Yield different logic equations, which can affect to a considerable degree the area and structure of the resulting circuit. For example, if we interchange the codes assigned to states C and D, then we obtain Table 9.9 and the following logic equations: equals x2 plus y1 y1 yx y2 y2 z equals xy1 y2. The implementation of the equations derived from this second stadia signet requires less than half the number of gates required for the circuit of Figure 9.17. Also, the second excitation function for y2 is independent of the state variables y1 and y2. It depends only on the input. Unfortunately, there is no simple procedure that can be used to arrive at an assignment yielding a minimal circuit under some well-defined cost criterion. Some trial and error is consequently necessary until an acceptable assignment is achieved. The state assignment problem and, in particular, its effect on the machine structure will be discussed extensively in Chapter 12. Introduction to Synchronous Sequential Circuits and Iterative Networks Table 9.10 State Table for a modulo 8 binary counter NS output PS X equals 0 X equals 1 X equals 0 X equals 1 S0 S1 S2 S3 S4 S5 S6 S7 S0 S1 S2 S3 S4 S5 S6 S7 S1 S2 S3 S4 S5 S6 S7 S0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 Figure 9.18 State diagram for a modulo 8 binary counter. A binary counter 0 slash 0 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 1 slash 1 1 slash 0 1 slash 0 1 slash 0 S 0 S 3 S 5 S 7 S 6 S 2 S 4 S 1 1 slash 0 1 slash 0 1 slash 0 1 slash 0 0 slash 0 0 slash 0 0 aught. A modulo 8 binary counter is to be designed with one input terminal and one output terminal. It should be capable of counting in the binary number system up to 7 and producing an output value 1 for every 8 input 1 values. After a count of 7 is reached, the next input value 1 will reset the counter to its initial state, i.e., to a count of 0. Let S0, S1, S7 respectively be the states of the counter after it has received 0, 1, 7 input values equal to 1. The state S0 that designates the 0 count is the initial state. Transitions occur between successive states only when the counter receives the input value 1. The state diagram and state table of the counter are shown in Figure 9.18 and Table 9.10. 9.4 Synthesis of Synchronous Sequential Circuits Table 9.11 Transition and Output Tables for a modulo 8 binary counter NS ZPS Y3 Y2 Y1 X equals 0 X equals 1 X equals 0 X equals 1000 0 0 0 0 0 1 0 0 0 0 1 0 0 1 0 10 0 0 0 10 0 10 0 11 0 0 0 11 0 11 100 0 0 1 0 0 1 0 0 1 0 1 0 0 1 0 1 1 0 1 1 1 0 0 0 1 1 0 1 1 0 1 1 1 0 0 1 1 1 1 1 1 0 0 0 0 1. From the correspondence between the states and the count, it is evident that no state in Table 9.10 is redundant. Also, since the counter has 8 states, a state assignment requires 3 state variables, having 23 is equal to 8 states. The states of these variables, starting from the all-zero position, are 0, 0, 0, 0, 0, 1. 111. The choice of assignment in this example should not be made arbitrarily since it determines the characteristics of the circuits and, in particular, specifies the code and number system in which the counter actually counts. Our objective is to design a counter that counts in the binary number system. Accordingly, the code assigned to each state must be a binary representation of the actual count associated with that state, that is S0000, S1001, S7111. The transition and output tables corresponding to the foregoing assignment are shown in Table 9.11. Implementing the counter with T flip-flops. To complete the synthesis, we need to choose an appropriate set of memory elements and derive their excitation functions. Let us select T flip-flops whose excitation requirements are specified by Table 9.5. Up to now, we have used a delay element whose output y, t, equals its excitation at time t-1 and, consequently, the transition table that specifies the required changes in the values of the y's yields the necessary current excitations as well. Table 9.11, however, does not yield the necessary excitations for the T flip-flops. Consider, for example, entries 0, 0, 0 at the top of the x equals 0 column and the bottom of the x equals 1 column. In the first case, the flip-flops remain unchanged, since the transitions are from S0 equals 0, 0, 0 to S0 equals 0, 0, 0. In the second case, however, the transitions are from S7 equals 111 to S0 equals 0, 0, 0, and, therefore, all 3 flip-flops must change state. Hence, while in the first case no excitations are needed, in the second case all 3 flip-flops must be triggered, i.e., T1 equals T2 equals T3 equals 1. Similarly, the transition from S5 equals 101 to S6 equals 110. Introduction to Synchronous Sequential Circuits and Iterative Networks Table 9.12 Excitation Table for T flip-flops T3 T2 T1 Y1. Figure 9.19 Schematic diagram of a modulo 8 binary counter with T flip-flops. Y3, Y2, Y1, X equals 0, X equals 1000, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 11, 0, 10, 0, 0, 0, 0, 0, 1, 0, 11, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. 0, 1, 1, 110 billion 1111 0, 0, 0, 111. T110, T310, T210, Z, Y2, Y3. Under X equals 1, requires Y3 to remain unchanged while Y1 and Y2 change state. Thus, from Table 9.5 it is evident that the required excitation is 0, 11. In the same manner, we can specify the required excitations for each transition and the excitation table shown in Table 9.12 results. This excitation table consists of 3 distinct maps specifying T1, T2, and T3 as functions of X, Y1, Y2, and Y3. The logic equations for the output and excitation functions are derived from Tables 9.11 and 9.12, respectively, and are as follows. Note that the code resulting from the binary state assignment is not cyclic, and thus the reader must be careful when reading the equations from the corresponding tables. Alternatively, it is possible to transform the tables into 3 maps and to determine the equations directly from these maps. T1 equals X, T2 equals XY1, T3 equals XY1Y2, Z equals XY1Y2 Y3. A schematic diagram from modulo 8 counter is shown in Figure 9.19. The clock has not been shown but is implicit in this and subsequent figures. A 1 appears on terminal Z whenever the total number of ones received at input line X is a multiple of 8. The actual count, modulo 8, of the number of incoming ones is given by the values of the state variables y1, y2, and y3, which have binary. 9.4 Synthesis of Synchronous Sequential Circuits Table 9.13 Excitation Table for SR Flip-flops X equals 0 X equals 1 Y3 Y2 Y1 S3 R3 S2 R2 S1 R1 S3 R3 S2 R2 S1 R1 0 0 0 0 0 1 0 10 0 11 100 billion 101 million 110,000 111 0 minus 0 minus 0 minus 0 minus minus 0 minus 0 minus 0 minus 0 0 minus 0 minus minus 0 minus 0 0 minus 0 minus minus 0 minus 0 0 minus 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 0 minus 0 minus 10 minus 0 minus 0 minus 0 0 1 0 minus 10 minus 0 0 1 0 minus 10 minus 0 0 1 10 0 1 10 0 1 10 0 1 10 0 1 weights 1, 2, and 4, respectively. For example, if 1, 0, and 1 equals 5 equals 21 equals y1, y2, y3, the number of incoming ones has been 5 modulo 8, i.e. 13. Implementing the counter with SR flip-flops. The modulo 8 binary counter can also be implemented using SR flip-flops. The excitation table, Table 9.13, is derived from the transition table, Table 9.11, and from the excitation requirements in Table 9.4. As an example, consider the specification of the transition from S5 equals 101 under X equals 1 to S6 equals 110. The value of y1 will change from 1 to 0 and, consequently, the flip-flop must be reset. From Table 9.4, it is evident that this is accomplished by setting S1 equals 0 and R1 equals 1, and thus the value 01 is entered in row 101, column S1R1 of Table 9.13. Similarly, y2 must change from 0 to 1, and the value 10 is entered in column S2R2, row 101. The value of y3, however, is to remain unchanged. Hence, R3 must not be 1 while S3 may be either 0 or 1, which means that the appropriate entry in row 101, column S3R3, is minus 0. The entire excitation table is specified in a similar way. Table 9.13 consists of 6 distinct maps for S1, R1, S2, R2, S3, and R3 as functions of the variables x, y1, y2, and y3. The logic equations for the excitation functions are S1xy1, S2xy1y2, S3xy1y2y3, R1xy1, R2xy1y2, R3xy1y2y3. The schematic diagram 3 corresponding to these equations is shown in Figure 9.20. 3. It is interesting to observe that the binary counter is an iterative network in the sense that, from the terminal viewpoint, each cell, containing a flip-flop and its associated logic, is indistinguishable from the others. Consequently, in order to design a modulo 16 counter, all that is necessary is to add a fourth identical cell in cascade with the 3 cells shown in Figure 9.20. Introduction to Synchronous Sequential Circuits and Iterative Networks Cell 1 Cell 2 Cell 3 S3 R3 Y31 Y3 S1 R1X Y101 Y1 S2 R2 Y21 Y2Z Y1. Figure 9.20 Schematic diagram of a modulo 8 binary counter with SR flip-flops. Figure 9.21 State diagram for a parity bit generator. A parity bit generator Y2 Y3. A, B, C di 0 barra 00 barra 00,1 barra 01 barra 00 barra 00 barra 01 barra 01 barra 0 e F G 0 barra 01 barra 01 barra 00,1 barra 1. A serial parity bit generator is a one-terminal circuit that receives coded message and adds a parity bit to every m-bit message so that the resulting outcome is an error-detecting coded message. The input values in our example are assumed to arrive in strings of 3 symbols, i.e., m equals 3, the strings being spaced apart by single time units. The parity bits are to be inserted in the appropriate spaces, and the resulting outcome is a continuous string of symbols, without spaces. Even parity will be used. That is, a parity bit 1 is to be inserted if, and only if the number of ones in the preceding string of 3 symbols is odd. The state diagram for the parity bit generator is shown in Figure 9.21. States B, D, and F correspond to even numbers of ones out of 1, 2, and 3 incoming input symbols, respectively. Similarly, states C, E, and G correspond to odd numbers of ones out of 1, 2, and 3 incoming input symbols, respectively. From either state F or state the machine goes to state A, regardless if the input symbol. Note that, in fact, the fourth input symbol is a blank, i.e. 0. Since the state diagram of Figure 9.21 contains 7 states, 3 state variables are needed for an assignment. However, since 3 state variables 9.4 Synthesis of Synchronous Sequential Circuits Table 9.14 State Table for a Parity Bit Generator NS, ZPS, Y1, Y2, Y3, X equals 0, X equals 1, X equals 0, X equals 1, A 0, 0, 0, B C 0, 0, B 0, 10 D E 0, 0, C 0, 11 E D 0, 0, D 1, 10, F G 0, 0, E 1, 11. GF00 F100 AA00 G101A A11 have a total of 8 states. One of the states will not be assigned, and so its entries in the corresponding state table may be considered as don't cares. We shall defer the study of the properties of incompletely specified machines to Chapter 10, however. The state table and a possible state assignment are shown in Table 9.14. The reader can verify that the following logic equations result if JK flip-flops are used as memory elements. Equals equals YY equals Y1, 1 plus K, 3Z equals YX, J1 Y2, J21, J3 XY XY2, 2Y3, K1 equals 2, K2 equals Y2 plus. Since the specification of the problem does not offer any clue as to which assignment to select, it may be chosen arbitrarily. The assignment shown in Table 9.14 has been selected so as to yield reduced dependency among the state variables. That is, J1 and K1 depend only on the second flip-flop, while J2 and K2 depend only on the first flip-flop. The method of selecting assignments that result in such circuit properties will be presented in Chapter 12. A sequential circuit as a control element in a computation. In the preceding examples, each sequential circuit received an input sequence and, in turn, produced an output sequence. This output sequence was the objective of the computation. However, many sequential circuits are used to control more complex computations. Indeed, the data for such computations do not even pass through the controlling circuit and are, therefore, not processed by it. The main role of a sequential circuit in the capacity of a control element is to streamline the computation by providing the appropriate control signals. Such circuits usually have a large number of inputs and outputs and, consequently, more informal design techniques simplify the design process considerably. The following example illustrates a simple computation in which a sequential circuit is the control element. Introduction to Synchronous Sequential Circuits and Iterative Networks Figure 9.22 A System to Compute for A plus B modulo 16. BK2L add X KK1 a 4444 A GB 4X Sequential Circuit MZ for A plus B 16. Initiate U. The schematic diagram in Figure 9.22 describes a digital system that computes the value of for A plus B modulo 16, where A and B are each a 4-bit binary number. In this figure, X is a register for containing 4 flip-flops while X is the number stored in X. The register can be loaded with either B or A plus X. The addition of A and X is performed by the 4-bit parallel adder, denoted ADD. Input B tox is the channel through which the 4-bit binary number B is loaded into the register in such a way that each bit enters the corresponding flip-flop. In general, if a number is loaded into the register, then it replaces the number presently stored in it. The slash followed by the number 4 across several lines in Fig. 9.22 indicates that each such line actually consists of 4 wires. The output L of the modulo 4 binary counter K is equal to 1 whenever the count is 3 modulo 4. The sequential circuit M has 2 inputs, an input U which initiates the computation and an input L that gives the count of K. It has 4 outputs, alpha, beta, gamma, Z, whose tasks are as follows. The outputs alpha and beta are control lines for loading the register X. Whenever alpha equals 1, the contents of B are transferred into X. Whenever beta equals 1, the values of X and are added and transferred back into X. The input of the counter is gamma. Hence, whenever gamma equals 1, the count of K increases by 1. Output Z assumes the value 1 whenever the final result is available in X, that is, whenever X equals, for A plus B, modulo 16. Output Z can itself be a control input of another register that is to receive the final result of the computation. However, to simplify the design, this register is not shown. Initially, the count of K is 0, as are the values of U and Z. When the value of U becomes 1, the computation starts by setting alpha equals 1, which causes B to be loaded into X. Next, A is added to X. This is accomplished by setting beta to 1 and, simultaneously, gamma to 1, so that the count in K will keep track of the number of times that has been added to X. After 4 such additions, Z assumes the value 1 and the computation is complete. At this point, the count in K is again 0 and, hence, K is ready for the start of the next computation. 4. A K-bit register is a group of K flip-flops such that each flip-flop can store 1 binary digit and the entire register thus stores a K-bit binary word. 9.4 Synthesis of synchronous sequential circuits. Figure 9.23 State diagram for circuit M. U equals 0 ABD 0 0 11 10 1 G equals 1 1 0 1 C minus slash Z equals 1 U equals 1 L equals 1 slash equals 1 dash slash equals 1 B L equals 0 B slash equals G equals. A compact state diagram for M is shown in figure 9.23. In this diagram, only some of the input and output symbols are shown, in particular, only those that change during the transition and are relevant for the transition in question. The clock is, as usual, omitted, although it is implicit. Initially, M is in state A. When U equals 1, M goes to state B without changing the output values. The pulse causes M to go to state C and to produce the output symbol next clock alpha equals 1, regardless of the other input symbols. This is indicated by the symbol minus slash alpha equals 1 on the line going from B to C. Register X contains the value of B now. If U is at 1, its value may change to 0 without affecting the computation. U is only needed to cause the transition from A to B and thus initiate the computation. Since L equals 0, the machine remains in state C, and for each clock pulse it produces 2 output values, beta equals 1 and gamma equals 1. These output values add A to X while advancing the count in K by 1 unit. After 3 such advances, L's value becomes 1 and M goes to state D. During this transition, A is added to X for the 4th time and K is set to 0. At this point, X equals, for A plus B, modulo 16 and, consequently, Z's value becomes 1. The system is now back in state A, ready to start a new computation. Let the state variables be assigned to the states of M as follows: a 0, 0, the Y1, Y2, 0, 1, 11, 10. This assignment is indicated in figure 9.23. Now BCD output functions can be derived directly from the state diagram without any tables or maps. For example, Alpha's value must become 1 whenever the state variable values are y1, y2 equals 0, 1. Thus, alpha equals y1, y2. Expressions for the other outputs are obtained in a similar manner. Beta equals gamma equals y1, y2, z equals y1, y2. The next state variables can be obtained with the aid of the transition table shown in Figure 9.24a and the corresponding maps shown in Figure 9.24b, assuming a realization of M by 2D flip-flops. In the transition table, some next state entries are variables, and the treatment of such variables is analogous to the Introduction to Synchronous Sequential Circuits and Iterative Networks Figure 9.24 implementing the sequential circuit M with D flip-flops. PSNS 1 y 2 y 1 y 2 0 0 0 0 1 11 11 1 L 10 0 0 y 1 y 2 y 1 y 2 0 1 0 1 1 1 L 0 0 minutos 0 0 1 1 1 0 y 1 y 2 A. Transition table. B. Maps for Y1 and Y2. Y1 ZB. GAUY Y22D2 clock LD1 clock Y2 Y1 clock Y1 C. Logic diagram. Treatment of the map-entered variables discussed in Section 4.6. When the present state of M is Y1 Y2 equals 0 0, the next state depends on U. That is, the next state is 0 0 if U equals 0 and 0 1 if U equals 1. Consequently, the next state entry in row 0 0 is 0 U. However, if the present state is 0, 1, then the next state is 11, regardless of the input values. Hence, the next state entry in row 0, 1 is 11. In a similar manner, we derive the entire transition table of Figure 9.24a. The maps in Figure 9.24b are obtained directly from the transition table. For example, the entry in row 11 of the transition table is y1, y2 equals 1L. Consequently, a 1 is entered in the Y1 map in cell 11 while an L is entered in the same cell in the Y2 map. Following the procedure for covering maps with map-entered variables, we obtain the following next state equations. Y1 equals Y2. Y2 equals Y1 Y2 plus 1 plus UI L Y2. It is useful to note that the next state equations can also be derived directly from the state diagram. Y1 is 1 in states C and D, hence it must change to 1 whenever the circuit is in either state B or C. Thus, from the state assignments. 9.5 An example of a computing machine 111 finite state control unit 1 head tape. Figure 9.25 An example of these states we obtain writing machine equals Y plus equals Y1 1 Y2 Y1 Y2 Y2. This equation is clearly identical to the one obtained above. Similarly, we can obtain the foregoing equation for Y2 just by inspecting the state diagram. A logic diagram for M is shown in Fig. 9.24c. 9.5 An example of a computing machine. We have been considering sequential machines as independent units possessing finite and limited memory capabilities, whose task is to produce pre-specified output sequences in response to the application of external input sequences. Such finite-state machines are known as non-writing, since they have no control on the external input and, in particular, cannot write or change their own input symbols. We shall subsequently consider a simple example of a writing machine, that is, a finite-state machine that is capable of modifying its own input symbols. Chapter 10 Capabilities, Minimization, and Transformation of Sequential Machines. This chapter extends some of the concepts introduced in Chapter 9 and presents important techniques for the synthesis of sequential machines and for other problems considered in later chapters. The first two sections are concerned with the general finite state model, its definition, capabilities, and limitations. The last two sections are concerned with the minimization of completely, as well as incompletely, specified machines. 10.1 The finite state model. Further definitions. Our attention will be focused primarily on deterministic machines, which possess the property that the next state S, t plus 1, is determined uniquely by the present state S, t, and the present input xt. Thus, S, t plus 1, xt, 10.1, equals delta S, t, where delta is called the state transition function. The value of the output z, t, is, in the most general case, a function of the present state S, t, and the inputs xt, i.e.
z, t, x, t. 10 lutego równa się
z, t, xt, 10.2, equals lambda s, t, where lambda is called the output function. A machine possessing properties in x, 10.1, and 10.2, is generally known as a Mealy machine. Another machine, known as a Moore machine, results when the output is a function of only the present state and is independent of the external input. In this case, z, t, 10.3, equals lambda s, t. Thus, we arrive at the following formal definition of a sequential machine. Definition 10.1 A synchronous sequential machine M is a quintuple, I, lambda, M equals O, S, delta, 307. Capabilities.
Capabilities, minimization, and transformation of sequential machines A, B, DC 0, 1/0, 1/0, 0/1, 1/0, 0, 1/0 Figure 10.1 state diagram for 0/0 machine M, where I, O, and S are finite non-empty sets of inputs, outputs, and states, respectively. Delta I times SS is the state transition function. Lambda is the output function such that lambda I times SO for Mealy machines, lambda SO for Moore machines. The Cartesian product I times S is the set containing all pairs of elements function delta associates with each pair, 2, Sj, n. The state transition, 2, Sj element Sk, from S called the next state. In a Mealy machine, the output function lambda associates with each pair, 2, Sj, an element OK from O, while in a Moore machine, a correspondence exists between the states and outputs. Input-output transformations consider the machine M, whose state diagram is given in Figure 10.1. It is a four-state machine, with one input variable and one output variable, for which A0, 1, A0, 1, S equals A, D, G equals B, C, O equals. Suppose that the initial state of M is A, and the input sequence is 110. Then the machine will proceed through states B and C and return to state A, while producing the output sequence 001. Thus, for an initial state A, the machine M transforms the input sequence 110 into 001. Similarly, for the same initial state, the input sequence 01100 is transformed into 00010. Since every computation involves some transformation of input-to-output sequences, a finite-state machine is capable of performing a variety of computations and solving a number of problems that can be expressed as a transformation of sequences. An important function of a sequential machine is to determine whether a given input sequence is a member of some pre-specified set of sequences. The machine accomplishes this function by accepting those sequences that are members of the set and rejecting those that are not. A machine, when started in its initial state, accepts an input sequence by producing an output value 1 as it receives the last symbol of that sequence. Thus, machine M accepts the 10.2 capabilities and limitations of finite-state machines. Sequences 110 and 0110 and rejects the sequence 01100 since its corresponding last output symbol is 0. The sequence detector of Fig. 9.15 can also be described as a machine that accepts those input sequences that are members of the set, all sequences whose last four symbols are 0101. The general problem of characterizing a machine's behavior by observing its input-output transformations is quite complex. Clearly, it is impractical to feed a machine with all possible input sequences in order to decide which it accepts. The problem increases in complexity if we wish to determine whether two arbitrary machines are related, in the sense that one machine accepts all the sequences accepted by the other. In this chapter, we shall present finite experiments to determine the characteristics, capabilities, and limitations of a machine and the relations between machines. These subjects are further developed in chapters 13, 14, and 16. Returning to the state diagram for M, we note that the application of input symbol 1 tom, when initially in state A, causes a transition to state B. We thus say that B is the one successor of A. In general, if an input sequence X takes a machine from state C to Sj, then Sj is said to be the X successor of C. For example, state D is the 111 successor of A. If M is known to be initially in either state B or C, the 10 successor will be either state A or D. We say that AD is the 10 successor of BC, if A is the 10 successor of B and D that of C. It is evident that no input sequence exists that can take M out of state D, and thus D is said to be a terminal state. Generally, a state is called terminal if either of the following is true. 1. The corresponding vertex in the state diagram is a sinc vertex, i.e., no outgoing arcs that emanate from it terminate in other vertices. 2. The corresponding vertex is a source, i.e., no arcs that emanate from other vertices terminate in it. A source state is clearly not accessible from any other state, and, similarly, no state is accessible from a sinc state. These are extreme examples of situations that limit the state transitions in a sequential machine. In other cases, certain subsets of states may not be reachable from other subsets of states, even if the machine does not contain any terminal state. If for every pair of states C, Sj of a machine M, there exists an input sequence that takes M from C to Sj, then M is said to be strongly connected. Clearly, any non-trivial machine that has terminal states is not strongly connected. 10.2 Capabilities and limitations of finite-state machines. At this point, having established several behavioral properties and synthesis procedures for finite-state machines, we turn our attention to some basic questions regarding the capabilities of these machines. What can a machine do? Are there any limitations on the type of input-output transformations that can be performed by a machine? What restrictions are imposed on the capabilities of capabilities, minimization, and transformation of sequential machines? The machine by the finiteness of the number of its states? Although a precise answer to these questions will be deferred to Chapter 16, we will point out the existence of problems not solvable by any finite-state machine and determine a characteristic of the transformations that are realizable by such machines. Let the input to an n-state machine be an arbitrarily long sequence of ones. In response, the machine will progress, starting from some initial state, through a succession of states, in accordance with its specified state transitions. Now, if we let the sequence be longer than n, the machine must eventually arrive at a state in which it has previously been. Consequently, from this point on, and because the input symbol remains the same, the machine must continue in a periodically repeating fashion. Clearly, for an n-state machine, the period cannot exceed n and could be smaller. Moreover, the transient time until the output reaches its periodic pattern cannot exceed the number of states n. The preceding result can easily be generalized to any arbitrary input sequence consisting of a string of repeated symbols. In every such case, the output will become periodic after a transient time no longer than n. This conclusion leads to many interesting results that exhibit the limitations of finite-state machines. For example, suppose that we want to design a machine which receives a long sequence of ones and is to produce output symbol 1 when and only when the number of input symbols that it has received so far is equal to k plus 1/2 for k equals 1, 2, 3. That is, the desired input-output transformation has the following form. Input equals 111111111111111. Output equals 10100010000001. Clearly, since the output sequence does not eventually become periodic, no finite-state machine can produce such an infinite sequence. In Section 9.1, we designed a serial adder capable of serially adding two binary numbers of arbitrary length. As another example demonstrating the limitations on the capabilities of finite-state machines, we shall show that the serial multiplication problem is not solvable by a fixed finite-state machine, i.e., no finite-state machine with a fixed number of states can multiply two arbitrarily large binary numbers. To prove the foregoing assertion, suppose that there does exist an n-state machine capable of serially multiplying any two binary numbers. Let us select 22p, 2p as each of the two numbers to be multiplied, so that 2p times 2p where equals p greater than n. The inputs are fed serially into the machine, least significant digits first. 2p is represented by a 1 followed by p zeros, and 22p by a 1 followed by 2p zeros. The input symbols are fed into the machine during the first p plus 1 time units, i.e., between t1 and tp plus 1, as shown in the table below. During this period, the machine produces zeros. At tp plus 1, the input stops, while the machine must go on producing p additional zeros followed by a 1. 10.3 State equivalence and machine minimization T2P plus 1, T2P, TP plus 1 TP, T2, T1 time 1 0, 0 0 first number 1,
0,
0 0 second number, 0, 0 1 0 0 product 0. During the time period between and the machine receives no T2P TP plus 1 bin input, but since p greater than n, it must have at one of the states twice during that time. Following the same line of argument as that pursued earlier, we are led to the conclusion that its output must be periodic and the period is smaller than p. Therefore, the machine will never produce the required output symbol 1. Note that for any two finite numbers, we can find a machine that is capable of multiplying them. However, the preceding result demonstrates that for every finite-state machine capable of performing serial multiplication, we can find finite numbers that it cannot multiply. The reason for this limitation stems from the limited memory available to the machine. While in performing addition, it only had to store information regarding a single-digit carry, in the multiplication problem, it must be able to store arbitrarily large partial products. In a similar manner, we can show that no finite-state machine with a fixed number of states can perform for arbitrarily large size blocks, the computation executed by the Turing machine of Section 9.5. As mentioned earlier, a more general and precise study of the capabilities and limitations of finite-state machines is deferred to Chapter 16, where they will be defined in terms of regular expressions. 10.3 State equivalence and machine minimization. In constructing the state diagram, or table, for a finite-state machine, it often happens that the diagram contains redundant states, i.e., states whose functions can be accomplished by other states. We note that the number of memory elements required for the realization of a machine is directly related to the number of states. Recall that, for an n-state machine, k equals log 2 n-state variables are needed for an assignment.
Consequently,
the minimization of the number of states does reduce the complexity and cost of the realization in many cases. Moreover, the testing of sequential machines, which is studied in Chapter 13, is considerably simpler when the machine does not contain redundant states. It is, therefore, desirable to develop techniques for transforming a given machine into another machine that has no redundant states, such that both have the same terminal behavior. Capabilities, minimization, and transformation of sequential machines. Table 10.1. A machine M1 and B, its state partitions NS, Z symbol partition PS X equals 0 X equals 1 P0, ABCDF, ABCD. E, 0F, 0E, 0F, 0D, 1D, 0b, 1b, 0p1, p2, p3, p4, AC, BDF, AC, BD, F, AC, E, BD, F, AC, E, BD, F, EFC, 0b, 0f, 1c, 0b, A. The K-equivalence of states. Two states, C and Sj, of a machine are distinguishable if and only if M there exists at least one finite input sequence that, when applied to M, causes different output sequences depending on whether C or Sj is the initial state. The sequence that distinguishes these states is called a distinguishing sequence for the pair C, Sj. If there is any uncertainty as to whether the state of M is C or Sj, then an application of the corresponding distinguishing sequence yields an output sequence that is sufficient to determine the unknown state uniquely. If there exists a distinguishing sequence of length k for the pair C, Sj, the states C, Sj are said to be k-distinguishable. As an example, consider pair B of the machine whose state table, A, M1 is shown in Table 10.1a. The pair A-B is 1 distinguishable, since the input symbol 1 applied to M1 when initially in state A yields the output symbol 1, and when initially in state B yields the output symbol 0. However, the pair A-E is 3 distinguishable since there is no input sequence of length less than 3 that distinguishes A from E. Furthermore, the only sequence of length 3 that is a distinguishing sequence for the pair A-E is x equals 111, and the output sequences corresponding to the initial states A and E are 100 and 101, respectively. Note that 1101 is also a sequence that distinguishes A from E, although it is not the shortest such sequence. An all-zero sequence will produce identical output sequences independently of whether the initial state is A or E. The concept of k-distinguishability leads directly to the definition of equivalency and equivalence. States that are not k-distinguishable are said to be k-equivalent. For example, states A and E of M1 are 2 equivalent. States that are k-equivalent are also R-equivalent for all or k. States that are k-equivalent for all k are said to be equivalent. Thus, we arrive at the following definition. Definition 10.2 The states C and Sj of machine M are said to be equivalent if and only if, for every possible input sequence, the same output sequence is produced regardless of whether C or Sj is the initial state. 10.3 State equivalence and machine minimization. Thus, C and Sj are equivalent, indicated by equals Sj. If there is no input shown, see theorem's C sequence that distinguishes them. It will be subsequently. 10.2. That states which are k-equivalent for all k less than or equal to n-1 are equivalent. Clearly follows see section 2.2, that if and then. It therefore equals is equals C Sj Sj Sk C Sk state equivalence and equivalence relation. In consequence of this characteristic, the set of states of the machine can be partitioned into disjoint subsets, known as equivalence classes, such that two states are in the same equivalence class if and only if they are equivalent, and are in different classes if and only if they are distinguishable. Definition 10.2 can be generalized to the case where C is a possible initial state in machine M1 while Sj is an initial state in machine M2, where both M1 and M2 have the same input alphabet. The procedure for determining the sets of equivalent states in a machine, i.e., the equivalence classes, ensues from the following property. If C and Sj are equivalent states, then their corresponding x successors, for all x, are also equivalent. This follows since otherwise it would be trivial to construct a distinguishing sequence for C, Sj, by first applying an input sequence that transfers the machine to the distinguishable successors of C and Sj. The minimization procedure. The object of this section is to describe a procedure for determining the sets of equivalent states of a specified machine M. The result sought is a partition on the states of M such that two states are in the same block if and only if they are equivalent. The first step is to partition the states of M into subsets such that all states in the same subset are one equivalent. This is accomplished by placing states having identical output symbols under all possible input symbols in the same subset. Clearly, two states that are in different subsets are distinguishable. As an example, consider the partitions of the states of machine M1 given in Table 10.1b. The first partition P0 corresponds to zero distinguishability and defines our initial ignorance regarding the response of the various states prior to the application of any input symbol. The partition P1 is obtained simply by inspecting the table and placing in the same block states having the same output symbols for all input symbols. Thus A, C, and E are in the same block since their output symbols for input symbols 0 and 1 are 0 and 1, respectively. A similar argument places B, D, and F in the other block. Clearly, P1 establishes the sets of states that are equivalent. The next step is to obtain the partition P2, whose blocks consist of the sets of states which are equivalent, that is, equivalent under any input sequence of length 2. This is accomplished by observing that two states are equivalent if and only if they are equivalent and their two successors for all possible 2 are also equivalent. Consequently, two states are placed in the same block of P2 if and only if they are in the same block of P1, and for each possible 2, their two successors are also contained in a block of P1. This step is carried out. Capabilities, minimization, and transformation of sequential machines. By splitting the blocks of P1 whenever their successors are not contained in a common block of P1, the 0 and 1 successors of AC are C and BDF, respectively, and since both are contained in common blocks of P1, the states in AC are equivalent and therefore AC constitutes a block in P2. The one successor of BDF is DBC, but since DB and C are not contained in a single block of P1, block BDF must be split into BD and F in such a way that the successors of the blocks in the refined 1 partition are equivalent. In a similar manner, P3 is obtained by splitting block AC of P2 into AC and E, since the 1 successors of A, C, and E are D, B, and F, which are not equivalent. In general, the partition PK plus 1 is obtained from PK by placing in the same that are in the same block of PK and whose block of those states PK plus 1 for successors every possible 2 are also in a common block of PK. This process places the states that are K plus 1 equivalent in the same block and states that are K plus 1 distinguishable in different blocks. Note that no state can belong to more than one block since this would make it distinguishable with respect to itself. If, for some k, pk plus 1 equals pk, then the process terminates and pk defines the sets of equivalent states of the machine. That is, all states contained in the same block of pk are equivalent while states belonging to different blocks are distinguishable. The partition pk is thus called the equivalence partition, and the foregoing procedure is referred to as the Moore reduction procedure. For the machine M1, the equivalence partition is P3 and therefore states A and C are equivalent, and so are B and D. Before proceeding with the minimization procedure, we shall prove two theorems to establish its validity and determine its length. Theorem 10.1 The equivalence partition is unique. Proof suppose that there exist two equivalence partitions PA and PB and that PA equals PB. Then there exist two states C and Sj that are in the same block of one partition and are not in the same block of the other. Since C and Sj are in different blocks of, say, PB, there exists at least one input sequence that distinguishes C from Sj and, therefore, they cannot be in the same block of PA. Diamond suit. Theorem 10.2 If two states 1 or C and Sj of machine M are distinguishable, then they are distinguishable by a sequence of length n minus less, where n is the number of states in M. Proof the partition P1 contains at least two blocks, otherwise M would be reducible to a combinational circuit that has only a single state. At each step, the partition pk plus 1 is smaller than or equal to pk. Recall that a partition pi less than or equal to pj if every block of pi is contained in a block of pj, e.g., p2 of M1 is smaller. 1a partition P is said to be a refinement of a partition Q if P is smaller than Q.
13 state equivalence and machine minimization machine equivalence table 12
10.3 State equivalence and machine minimization machine equivalence table 10.2 machine M1
13 state equivalence and machine minimization machine equivalence table 12 machine MNNS zen miden ena XXP es miden alpha vita gamma ena vita alpha miden delta ena gamma delta miden delta gamma miden alpha miden.
Then P1. If is smaller than pk, then it contains at least one more block pk plus 1 than pk. However, since the number of blocks is limited to n, at most n-1 partitions can be generated in the reduction procedure, and thus, if C and Sj are distinguishable, then they are distinguishable by a sequence of length n-1 or smaller. Diamond suit it can be shown, see problem 10.15, that the above is indeed the least upper bound. Before proceeding with the determination of the minimal machine that is equivalent to M1, we shall define precisely what we mean by equivalent and minimal machines. Definition 10.32 machines M1 and M2 are said to be equivalent if, and only if for every state in M1 there is a corresponding equivalent state in M2 and vice versa. Defines the minimum or the equivalence partition has been shown to be unique. Thus, the number of blocks in the equivalence partition of a machine M number of states that any machine equivalent to M must have. The machine that contains no equivalent states and is equivalent to M is called the minimal, reduced form of M. If we denote the blocks of the equivalence partition P3 of by alpha, beta, gamma, M1 and delta, corresponding respectively to AC, E, BD, and F, we obtain the machine M** operator 1, table 10.2. In constructing M** operator 1, we specify the one successor of alpha to be gamma, since the one successor of AC is BD, and so on. In this manner, M** operator 1 is specified to duplicate the state transitions and response of M1 and, therefore, is equivalent to it. In addition, since it has been generated by the equivalence partition of M1, it is its minimal form. Example: we shall illustrate the reduction procedure further by applying it to a machine M2, table 10.3, and finding its minimal form, the blocks. Capabilities, minimization, and transformation of sequential machines of the equivalence partition P for our denoted alpha, operator, and the reduced beta, machine M2, table 10.4, results. Table 10.3, A, machine M2 and B, its state partition symbol partition NS, Z, A, B, C, D, F, G, 0, 1, P0, X equals E, X equals C, PS, A, B, C, D, F, G, E, P1, 0, A, 0, AF, B, C, D, G, E, P2, 0, B, C, A, 0, AF, BD, CG, E, P3, 0, CB, G, 0, A, F, BD, CG, E, P4, 0, DG, A, 0, A, F, BD, CG, E, P5, 1, EF, B, 0, FE, 0, D, 0, B, 0, GD, G, 0, A, table 10.4 machine M** operator 2 NS, Z0, 1 X equals delta, PS. A, miden alpha, F, miden vita gamma, BD.
A, 00 alpha, F, 00 beta gamma, BD, delta, 00 gamma alpha, CG, delta gamma, 0 delta, 0, E, beta, 1 gamma, 0. The selection of labels alpha, beta, assigned to the blocks of P4 is obviously
The selection of labels alpha, beta, assigned to the blocks of P4 is obviously arbitrary. A different assignment of labels would have described a machine with the same behavioral properties. In general, if one machine can be obtained from the other by relabeling its states, then they are said to be isomorphic to each other. The foregoing results lead to the following basic conclusion. To every machine M, there corresponds a minimal machine M asterisk operator that is equivalento M and is unique up to isomorphism. The detection of isomorphism is not always easy and is best accomplished by using a canonical representation for a machine. Such a representation is obtained by selecting a state, preferably the starting state if specified, and labeling it A. The next labels are selected in such a way that when successive rows of a table, starting in A and going down through B, C, etc., are read from left to right. The first occurrence of each new label will be in alphabetical order. Whenever a machine is given in this canonical representation, it is said to be in standard form. Clearly, when the starting state of a reduced machine is specified, its standard form is unique. 10.4 Simplification of incompletely specified machines. Table 10.5 Standard form for M asterisk operator 2 and S. Z0 1x equals PS 00 alpha AB C 10 BD E delta CE 0 C 0 beta DB 0 E 0 gamma EC 0 A 0. The transformation of a machine into its standard form will be illustrated by means of M asterisk operator 2. Denoting alpha by A implies that its zero successor must be denoted B, because it is the first occurrence of a new label. Similarly, its one successor delta must be denoted C. Row B, i.e., must be relabeled next. Its first entry is beta and, since it is a new label, it is denoted D. Similarly, gamma is denoted E, and the standard form of Table 10.5 results. When the starting states are not specified, the detection of isomorphism is, in general, not as simple. If the number of states is not too large, however, isomorphism can be detected by inspecting the state diagrams of the machines. The necessary and sufficient condition for two machines to be isomorphic to each other is that their state diagrams are identical except for the labeling of their vertices. 10.4 Simplification of incompletely specified machines. In practice, it often happens that various combinations of states and input symbols are not possible. For example, the machine of Table 9.15, when in state A, will never receive input symbol 0 and, consequently, the corresponding transition and its associated output symbol may be left unspecified. In other situations, the state transitions are completely defined, but for some combinations of states and input symbols, the output values may not be critical and thus are left unspecified. Such machines are said to be incompletely specified. The determination of their properties and methods for simplifying them are the subject of this section. 12.2 State assignments using partitions. State assignment and the reduction in dependency of the state variables to the structure of a sequential machine. These factors will be shown to affect the complexity and cost of the final circuits as well. 12.2 State Chapter 12 Structure of Sequential Machines. One of the main problems in the synthesis of sequential machines is that of assigning combinations of state variable values to the states of the machine. This assignment determines the complexity and structure of the circuit which realizes the machine. Various restrictions and requirements may be imposed on the state assignment, depending on the design objectives and intended use of the circuit. It may be desirable, for example, to construct it using a minimum amount of logic, or to build it from an interconnection of smaller circuits, and so on. The structure of a sequential machine includes the manner in which a machine can be realized from a set of smaller component machines as well as the functional dependencies of its state and output. Variables. It is our aim in this chapter to study the state assignment problem and how it affects the structure and complexity of sequential machines. 12.1 Introductory example. The close relationship between the state assignment problem and the structure of sequential machines will be demonstrated by means of the machine M1 shown in Table 12.1. Two possible state assignments form one are shown in Table 12.2. The logic equations corresponding to assignment alpha, which are derived from the excitation and output tables, are y1 igual a x más más 1 igual a y1 x y f1.
y1 equals x plus 1 equals y1 x y f1, x, y2, z equals y2 y1 x y2 f2, x, y1, x y2 f0, x, y2. From these equations, it is evident that y1 is a function of y1 and of the external input and is independent.
From these equations, it is evident that y1 is a function of y1 and of the external input and is independent of y2. However, y2 depends on the external input as well as y1 and y2. The output z is a function of x and y2 only. The circuit diagram of M1 is shown in Figure 12.1a. The dependency of the next state variables and the output is illustrated by the block diagram of Fig. 12.1b, where 372. 12.1 Introductory example Table 12.1 Machine M1 NS ZPS x equals 0 x equals 1 x equals 0 x equals 1 a d0 1 b a c0 0 ccb 0 0 dca 0 1 Table 12.2 Excitation and output tables for M1 y1 y2 z y1 y2 x equals 0 x equals 1 x equals 0. X equals 1 A B C D 0 0 0 1 11 10 0 0 0 0 11 11 10 11 0 1 0 0 0 0 0 0 1 0 0 1 A. Assignment alpha y1 y2 z y1 y2 x equals 0 x equals 1 x equals 0 x equals 1 a b c d 0 0 0 1 10 11 0 0 0 0 10 10 11 10 0 1 0 0 0 0 0 0 1 0 0 1 b. Assignment beta zy1x y1 y2 y2 fig 12.1 First realization of M1. A. Circuit diagram. F1, X, y1, Z1, X, y1, F2, X, y1, y2, 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 F0, X, y2, B. Block diagram. Structure of sequential machines, Figure 12.2 Second realization of M1. X, X, Z, X, X, F1, X, y1, 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 A. Circuit diagram. y2, Z, y1, y1, B. Block diagram. F2, X, y2, 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 F0, X, y1, y2, y2, X. For example, the block labeled F1, X, Y1 corresponds to the combinational logic associated with memory element Y1 and so on. The logic equations corresponding to assignment beta, shown in Table 12.2b, are y1 equals x equals plus equals 1 equals y1 y1 xy f1 x y2 z equals 2 plus y2 xy f2 x y2.
2 igual a xy1 y xy1 y 2 f0, x y 1.
In this case, y1 is independent of y2 and y2 is independent of y1. In other words, the next value of each state variable can be computed from its present value and the value of the present input, regardless of the value of the other state variable. The dependency of the output function, however, has increased in comparison with its dependency in assignment alpha, shown in Table 12.2a. The circuit and block diagrams corresponding to assignment beta are shown in Figure 12.2. The preceding two realizations of machine M1 clearly demonstrate that the choice of assignment affects the complexity of the circuit and determines the dependency of the next state variables and the overall structure of the machine. Our objective in this chapter is to investigate the relationship of the 12.2 state assignments using partitions, state assignment, and the reduction in dependency of the state variables to the structure of a sequential machine. These factors will be shown to affect the complexity and cost of the final circuits as well. 12.2 state assignments using partitions. In this section, we shall derive necessary and sufficient conditions for asequential machinem to have assignments that result in reduced dependencies among the state variables. Such assignments generally yield simpler logic equations and circuits. They are also the fundamental means by which machine decompositions are obtained. Closed partitions. Let machine M have a set of n states and a set of S equals K equals S1, S2, Sn, P input symbols I, then log 2 state variables and L equals I1 equals as I2, IPN. Log 2 input variables are needed for a complete assignment, where Pg defined as the smallest integer equal to or greater than G. Each of the K next state variables depends, in general, on the external inputs x1, x2, xl, and the K state variables, i.e. phi xl, 1, 2.
Igual a y, y1, y2, yk, x1, x2, k.
Our objective is to obtain assignments in which the values of one or more subsets of the next state variables can be determined independently of the values of the remaining variables, that is, assignments which yield logic equations for the variables y1, y2, year, where 1 less than or equal to r less than k, that are independent of the remaining k minus r variables. Thus, phi xl, 1, 2.
En havali I, ein adai, esin estai, a.
The subset of state variables whose values are independent of y1, y2, year of the values year plus 1, year plus 2. Yk is said to be a self-dependent subset, and an assignment that yields such a subset is said to possess self-dependent subsets. Assignments alpha and beta of machine M1 both have this property. The state assignment problem may be viewed as either a coding problem or a partitioning problem. In viewing the state assignment as a coding problem, a distinct code is assigned to each row, state, of the state table. From the partitioning point of view, which we shall adopt in this chapter, each state variable E induces a partition tie on the set of states of the machine, such that two states are in the same block of tau I if, and only if they are assigned the same value of E. For example, in assignment alpha for machine M1, y1 equals 0 for states A and B, and y1 equals 1 for states C and D. Hence, y1 induces the partition tau1 equals A, B, C, D, see definition 2.1, on the states of M1. Similarly, y2 induces the partition tau2 equals A, D, B, C. Clearly, if the assignment is such that each structure of sequential machine state has a unique code, then the product of the K partitions tau1, tau2, tau-K corresponding to y1, y2, yk is equal to 0, that is,
taf ena, staf dio, taf kp, miven.
We have shown how an assignment induces a set of partitions whose product is the 0 partition pi, 0. The inverse process, that of assigning the values of the state variables to distinguish the blocks of a set of partitions, is the process of significance in the synthesis procedure. Given a partition tau with hashtag tau, blocks on the set of states of M. To distinguish between these blocks, it is necessary to select r equals log 2 hashtag tau state variables and assign a distinct combination of these variables to each block of tau. That is, all the states in each block are assigned the same values of y1, y2, year. Each partition on the states of M provides some information regarding M state.
If empazesis to partisans taf ena en taf dio such that taf en ang taf dio then taf dio provides more information than taf ena.
Clearly, the zero partition provides all the necessary information, since knowledge of which block of pi, 0, the machine is in is sufficient to determine the state of M uniquely. Thus, to obtain an assignment form such that each state has a distinct code, it is necessary to assign the values of the state variables in such a way that they distinguish between the blocks of a set of partitions whose product is the zero partition. Example for machine M1, the product of the partitions equals A, B, if we assign D in tau1c and C, is 0, i.e., pi 0. Hence, y1 equals A away D tau2 equals B, tau2b, tau1 such as to distinguish block from block D, and y2 in such, A, C, a way as to distinguish the blocks of tau2. Then each state of will have AM1 distinct code. One such assignment is beta, shown in Table 12.2b. Definition 12.1a partition pi on the set of states of a sequential machine M is said to be closed if, for every two states C and Sj, which are in the same block of pi, and any input symbolic in I, the states xc and xsj are in a common block of pi. Xc denotes the successor of C. Example for machine M1, Table 12.1. The partitions equals A, B, of DVC, pi1c, and C are closed. Point 1 the 0, and 1 successors equals A, C, D, pi2b, A are A and D, respectively, while the only successor of D, B, B is C. If we denote the blocks of pi2, A, C, and D by P and A, B, Q respectively, then we may describe the successor relationships of these blocks by means of the graph of Figure 12.3. Clearly, knowledge of the present block of M1 and the input symbol is sufficient to determine the next block. 1 in general, we shall reserve pi to denote closed partitions while tau, theta, etc. will denote arbitrary partitions. 12.2 State assignments using partitions uniquely. We shall subsequently say that a machine is in a block when we mean that it is in one of the states contained in the block. 1 QP001 A, C, a P. Figure 12.3 Successor relationships of the blocks of the partition B, D, Q equals pi2 reduction of the functional dependency of the state variables. We shall now establish the relationship between closed partitions and their reduction in functional dependency of state variables. Theorem 12.1. Let M be a sequential machine with k state variables y1, y2, yk. If there exists a closed partition pi on the states of M, and if our state variables, where equals log 2 hashtag pi, are assigned to the blocks of pi, such that all the states contained in each block are assigned the same values of y1, y2, year, then the next state variables y1, y2, year are independent of the remaining k minus r variables. Conversely, if the first are next state variables y1, y2, year 1 less than or equal to r less than k, can be determined from the values of the inputs and the first are state variables, independently of the values of the remaining k minus r variables. Then there exists a closed partition pi on the states of M such that two states, C and Sj, are in the same block of pi if, and only if they are assigned the same values of the first r variables. Proof: since each block of pi is assigned the same values of the variables y1, y2, year, and since pi is closed, knowledge of the present block of pi and the present input values is sufficient to determine the next block of pi. In other words, knowledge of the present values of y1, y2, year, and of the present input values is sufficient to determine the values of y1, y2, year, regardless of the values of the remaining variables. To prove the converse, form a partition pi on the states of M such that all the states with the same assigned values of y1, y2, year are in the same block of pi. To prove that pi is closed, consider two states C and Sj that belong to the same block of pi. Each of these states has the same assigned values of the first R variables, and since these variables are independent of the values of the remaining ones, an application of the same input sequence to both C and Sj causes the same change in the values of the first R variables for these two states. Therefore, for each value of IC, the successors xc and xsj have the same assignment of values for the first R variables and, consequently, are contained in the same block of pi. Thus, pi is closed. Diamond suit. Structure of sequential machines. Example for machine M1, the partitions V and equals A, beta D equals to pi1c, pi2c, are closed. Since y1 an assignment has been assigned A, B, D distinguish the blocks of pi1, it is independent of y2. Similarly, since y2 has been assigned to distinguish the blocks of pi2, it is independent of y1. Theorem 12.1 actually states a necessary and sufficient condition for the decomposition of sequential machines: the existence of a partition tau and a closed partition pi on the set of states of a machine M, such that pi tau equals pi 0, guarantees that M can be composed of two-component machines connected in series. The first component in the connection consists of log2 hashtag pi memory elements and their excitation circuitry, corresponding to the state variables assigned to distinguish the blocks of pi. Since these variables are independent of the remaining variables, the first component is often referred to as the independent component. The second component in the serial connection, also referred to as the dependent component, contains log2 hashtag tau memory elements, corresponding to the state variables assigned to distinguish the blocks of tau. We shall refer to the independent component as the predecessor machine and the dependent component as the successor machine. It is often convenient to view the predecessor machine as the component that distinguishes between the blocks of pi, and the successor machine as the component that distinguishes between the states within the blocks of pi. The existence of two closed partitions on the states of M such that their product is 0, i.e., pi1, pi2 equals pi 0, implies that M can be composed of two components operating in parallel, independently of each other. One component consists of log2 hashtag pi1 memory elements, corresponding to the variables assigned to distinguish the blocks of pi1. The second component consists of log2 hashtag pi2 memory elements, corresponding to the variables assigned to distinguish blocks of pi2. The preceding arguments can thus be summarized as follows. An n-state machine M can be decomposed into two independent components operating in parallel if, and only if there exist two non-trivial closed partitions pi1 and pi2 on the states of M, such that pi1 be the op mi then. This decomposition requires a minimal number, i.e., log2n, of state variables if and only if log2 hashtag pi1, log2 hashtag pi2, log2 plus equals n. Example: consider the machine M2 given in Table 12.3. It can be shown that M2 has 7 closed partitions, which are listed in Figure 12.4. Since M2 has 8 states, 3 state variables are needed for an assignment. The existence of the closed partition pi5 suggests that M2 can be realized as two-component machines connected in series. The predecessor component has 2 state variables, y1 and y2, which are assigned to the blocks of pi5 and 12.2 state assignments using partitions. Table 12.3 machine M2 and SPS x equals 0, H x equals 1 BZA 0 BFA 0 CGD 0 DEC 1 EAC 0 FCD 0 GBA 0 HDB 0
A, B, C, D, E, F, G, H, B, moving. A, 8 P mi de P and a B, C, D, E,
A, B, C, D, E, F, G, H pi, 0, equals A, equals H, pi 0 pi 1 B, C, D, E, F, G, pi 2 equals A, D, E, H, B, C, F, G, pi 3 equals A, D, B, C, F, G, E, H, pi 4 equals A, D, E, H, B, C, F, G, pi 5 equals A, D, B, C, E, H, F, G, pi 6 equals A, B, C, D, E, F, G, H equals pi, I fig 12.4 closed partitions for M2. Consequently, are independent of Y3, while the successor component has a single variable, Y3, which distinguishes the states in the blocks of pi 5. Maximal reduction in the dependency of state variables would be achieved if we could find 3 two-block closed partitions whose product is 0.
Maximal reduction in the dependency of state variables would be achieved if we could find 3 two-block closed partitions whose product is 0. In such a case, each state variable would be independent of the remaining 2 variables, and the machine would be realized as a parallel connection of 3 component machines. It is evident, however, from the list of non-trivial closed partitions of M2 that only 2 two-block partitions can be found, namely pi 1 and pi 2. In fact, since each non-trivial closed partition is greater than pi 5, no combination of closed partitions can be found whose product is 0. Therefore, we must select a partition tau such that P1 P2 ktaf P mi ven.
Pi 1 pi 2 tau equals pi 0. One possible such partition is tau equals A, F, D, G, H, C, D, E. Assigning Y1 to distinguish the blocks of pi 1, Y2 to distinguish the blocks of pi 2, and Y3 to distinguish the blocks of tau results in the assignment given in Table 12.4. Clearly,
Y1 and Y2, which are assigned to the blocks of closed partitions, will be self-dependent, while Y3, which is assigned to the blocks. Structure of sequential machines, Table 12.4 Excitation and output table for M2 Y1 Y2 Y3 Y1 Y2 Y3 X equals 0 X equals 1 ZA 0 0 0 100 0 10 0 B 0 10 111,000 0 C 0 11 110 0 0 10 D 0 0 1 1 0 10 11 1 E 101 million and 11 0 F 1 11 0 11 0010 G 110 million 10,000 0 H 100 million 1,000 and 10 0 of tau will be a function of the external input and all 3 state variables. The logic equations derived from Table 12.4 are y1 equals xy1, y2 equals xy2 plus. Igual a más x xy2, z igual a y 3 más y más x y 3 xy.
Equals plus x xy2. Z equals y3 plus y plus x y3 y3 y1 y2 y1 y2 y3 y1 y2 y3 y1 y2 y3 1 y2 y3. The corresponding schematic diagram is shown in Fig 12.5. Logic
igual a más x xy2, z igual a y 3 más y más x y 3 xy 3 y 1 y 2 y 1 y 2 y 3 y 1 y 2 y 3 y 1 y 2 y 3, 1 y 2 y 3. The corresponding schematic diagram is shown in Figure 12.5. Logic ZX, Y1 logic, Y2 logic, Y3 logic. Figure 12.5 schematic diagram for M2. 12.3 The lattice of closed partitions.